Welcome to a journey through the cosmos. A journey where time moves slowly, where distances are beyond imagination, and where the universe paints with colors we're only beginning to understand. Tonight, we're going to drift through space together, exploring some of the most beautiful phenomena in our universe. Nebulae, these cosmic clouds, these stellar nurseries, these monuments to stars both born and dying. They exist in a realm so vast, so peaceful, that our earthly concerns seem to fade away in their presence. So, settle in, get comfortable, let your breathing slow, and allow yourself to float among the stars. The word nebula comes from the Latin word for cloud or mist. And truly, that's what these cosmic wonders are, clouds. But not clouds of water vapor like those that drift across our skies here on Earth. No, these are clouds made of hydrogen, helium, dust, and plasma, scattered across distances so enormous that light itself takes years to cross them. Imagine a cloud so large that our entire solar system, from the sun to the farthest reaches of the Kuiper Belt, will be nothing more than a tiny speck within it. That's the scale we're dealing with when we speak of nebulae. For most of human history, nebulae were mysteries. Ancient astronomers looked up at the night sky and saw fuzzy patches of light, smudges against the darkness. They didn't know what these objects were. They couldn't have known. Without telescopes, without the ability to see beyond what our eyes could perceive, these cosmic clouds remained enigmatic, beautiful, but unknowable. It wasn't until the 1600s that everything began to change. The telescope opened up the heavens in ways that must have seemed almost magical. Suddenly, astronomers could see deeper into space. They could observe details that had been hidden for all of human existence. And what they found were nebulae. Dozens of them, then hundreds, then thousands. But here's something fascinating. Even with telescopes, astronomers still didn't fully understand what they were looking at. For centuries, the term nebula was used to describe almost anything in the sky that appeared fuzzy or cloud-like. Distant galaxies, star clusters, actual nebulae, they were all grouped together under this one name. It was only in the 20th century, as our technology improved and our understanding deepened, that we began to distinguish between these different objects. We learned that some of those fuzzy patches weren't clouds of gas at all. They were entire galaxies, island universes of billions of stars, so far away that they appeared as nothing more than soft glows in our telescopes. But true nebulae, these clouds of gas and dust within our own Milky Way galaxy, they became objects of intense fascination, because within them, we discovered something profound, the story of stellar birth and death. You see, nebulae aren't just beautiful. They're not just cosmic decorations scattered across the void. They're integral to the life cycle of stars. They're the places where stars are born, and the monuments left behind when stars die. Think about that for a moment. Every star you've ever seen in the night sky, every point of light that has ever caught your eye, was born in a nebula, including our own Sunday. 5 billion years ago, in a cloud of gas and dust, not unlike the nebulae we'll explore tonight, our star began its journey. Gravity pulled material together, slowly, patiently, over millions of years, until finally, the pressure and temperature at the core became so intense that nuclear fusion ignited, and the sun was born. Right now, at this very moment, this same process is happening in nebulae across our galaxy. Stars are being born, and in some nebulae, in those regions we call stellar nurseries, hundreds or even thousands of stars might be forming at once. It's a process that takes time, so much time that from a human perspective, it seems almost frozen. If you could watch a nebula for your entire lifetime, you would see virtually no change. The timescales of stellar birth are measured in millions of years. The clouds drift, the gas slowly collapses under its own gravity, but so gradually that even with our most sensitive instruments, we can barely detect the motion. And yet, it's happening. Constantly. Patiently. The universe doesn't rush. Now, while some nebulae are birthplaces, others are monuments. When massive stars reach the end of their lives, when they've burned through all their fuel, they don't simply fade away. They explode. Violently. Catastrophically. In events we call supernovae. And what remains after such an explosion? A nebula. An expanding shell of gas and dust, glowing from the energy of the explosion, spreading out into space at thousands of kilometers per second. These are called supernova remnants, and they're some of the most spectacular nebulae we can observe. But even this destruction is part of creation, because the material expelled by these dying stars, the carbon, the oxygen, the iron, all the heavier elements created in the star's core, this material becomes part of new nebulae. It mixes with the hydrogen and helium, enriching the clouds. And from these enriched clouds, new stars form. Stars with planets. Planets that might harbor life. In fact, almost every atom in your body right now, every atom except for hydrogen, was created inside a star. And when that star died, it released those atoms into space, into a nebula, where they eventually became part of the cloud that formed our sun and earth. We are, quite literally, made of stardust, made of nebulae. The beauty of nebulae isn't just in their appearance, though they are breathtakingly beautiful. It's in what they represent. Nebulae are proof that the universe is in constant transformation, that nothing is permanent, that death leads to birth, and birth eventually leads to death, in an endless cosmic cycle that has been ongoing for billions of years and will continue for billions more. They remind us of our place in this vast universe. We're part of this cycle, part of this story. Temporary, yes, but connected to something infinitely larger and infinitely older than ourselves. As we continue our journey tonight, we'll explore different types of nebulae. We'll visit stellar nurseries where stars are just beginning their lives. We'll drift through planetary nebulae, the gentle deaths of stars like our sun. We'll witness the violent beauty of supernova remnants, and we'll see how all of these connect, how they're all part of the same grand story. But for now, just let yourself rest with this thought. Somewhere out there, in the depths of space, in clouds of gas and dust spanning light years, stars are being born. Right now, this moment, and somewhere else, a star is dying, releasing its material back into space, back into the cosmic clouds, to begin the cycle again. The universe breathes, in and out, birth and death, creation and transformation, forever. Rest now. Let the vastness of space cradle you. Let the patience of the cosmos slow your thoughts. And when you're ready, we'll continue deeper into the nebulae. Among all the types of nebulae scattered across our galaxy, emission nebulae are perhaps the most vibrant, the most colorful, the most visually stunning. These are the nebulae that glow with their own light, illuminated from within by the very stars they helped create. Imagine a cloud of hydrogen gas, vast and cold, drifting through the darkness of space. For millions of years, it exists in silence, invisible to our eyes. But then, deep within its core, something changes. Gravity begins to pull the gas together. Slowly, over eons, a star is born. And when that star ignites, when nuclear fusion begins in its core, everything transforms. The newborn star pours out radiation, ultraviolet light, intense and energetic, floods into the surrounding gas cloud. And this ultraviolet light does something remarkable. It ionizes the hydrogen atoms in the nebula. It strips away their electrons, energizing the gas, causing it to glow. This is an emission nebula, a cloud that shines not because it's reflecting light from somewhere else, but because it's actively emitting light of its own. The process is beautiful in its simplicity. When those hydrogen atoms recapture their lost electrons, they release energy in the form of light. Specifically, they emit light in a deep red wavelength, a color we call hydrogen alpha. This is why so many emission nebulae appear predominantly red in photographs. That crimson glow is the signature of hydrogen recombining with its electrons over and over, billions upon billions of times per second, throughout the entire nebula. But hydrogen isn't the only element at play. Emission nebulae also contain oxygen, nitrogen, sulfur, and other elements. Each of these elements, when ionized and then recombined, emits light at its own specific wavelengths. Oxygen gives us teal and green hues. Sulfur contributes deeper reds. Nitrogen adds touches of orange and red. The result is a cosmic palette of colors, each one telling us something about the composition of the nebula, about the elements present in that particular cloud, about the conditions and temperatures within it. One of the most famous emission nebulae is the Orion Nebula. Located about 1,344 light-years from Earth, it's visible to the naked eye as a fuzzy patch in Orion's sword, that line of stars hanging below the 3 stars of Orion's belt. Through binoculars or a small telescope, it reveals itself as something extraordinary, a glowing cloud of gas and dust, roughly 24 light-years across. Within the Orion Nebula, stars are being born right now, thousands of them. The nebula contains enough material to create thousands of stars like our Sun, and it's in the process of doing exactly that. At its heart lies the Trapezium Cluster, a group of young, massive, incredibly hot stars. These stars are less than 1 million years old, babies by cosmic standards, and it's their intense ultraviolet radiation that causes the entire nebula to glow. If you could visit the Orion Nebula, if you could somehow float within its vast expanse, you wouldn't see the vibrant colors that appear in photographs. Our eyes aren't sensitive enough. The light would appear dimmer, more subtle, perhaps a pale, greenish glow. But you would see something else, the sheer scale of it. The way the gas stretches in every direction, forming intricate structures, pillars, waves, cavities carved out by stellar winds. And you would see the stars. So many stars. Some already formed, burning brightly. Others still cocooned in their natal clouds, their lights struggling to break through the dust. And throughout it all, the gas would be glowing, energized, alive with the light of stellar birth. Another remarkable emission nebula is the Lagoon Nebula, catalogued as Messier 8. Located about 4,000 light-years away in the constellation Sagittarius, it's one of only 2 star-forming nebulae visible to the naked eye from mid-northern latitudes. The Lagoon Nebula spans about 110 light-years across and contains several regions of active star formation. What makes the Lagoon Nebula particularly fascinating is its structure. It's not a uniform cloud of gas. Instead, it's filled with dark lanes of dust that divide the glowing regions, creating the lagoon-like appearance that gives the nebula its name. These dark lanes aren't empty. They're dense concentrations of dust, so thick that they block the light from the glowing gas behind them. They're silhouetted against the brightness, creating contrast, adding depth to our view. Within these dark lanes, hidden from direct view, stars are forming. Protected by their dusty cocoons, sheltered from the intense radiation of nearby massive stars, young stellar objects grow slowly, gathering mass, preparing for the moment when they'll ignite and join the cosmic display. The Lagoon Nebula also contains something called a Bok globule, a small, dark cloud of dense dust and gas. These globules are stellar nurseries in their own right, compact regions where individual stars or small groups of stars are forming in isolation. They appear as dark spots against the glowing nebula, mysterious and pregnant with potential. Then there's the Eagle Nebula, home to one of the most iconic astronomical images ever captured, the the pillars of creation. This Emission Nebula, located about 7,000 light-years away, is a vast region of active star formation. The pillars themselves are columns of gas and dust, each several light-years tall, sculpted by the radiation and stellar winds from nearby young stars. These pillars are beautiful, yes, but they're also temporary. The same forces that make them glow, the same ultraviolet radiation that illuminates their edges, is also eroding them. Slowly but inexorably, the pillars are being worn away. The gas is being dispersed. In a few million years, they'll be gone, their materials scattered into space, perhaps to form new stars elsewhere. But even as they're being destroyed, they're also creating. Deep within the pillars, protected from the harsh radiation by the surrounding gas and dust, new stars are forming. Infrared observations have revealed dense knots within the pillars, regions where gravity is winning the battle against the outward pressure, where stars are coalescing. It's a beautiful paradox. The same process that's destroying the pillars is also driving star formation within them. Creation and destruction, happening simultaneously, inseparably linked. Emission nebulae come in many sizes. Some are relatively small, just a few light-years across. Others are enormous, spanning hundreds of light-years. The Tarantula Nebula, located not in our Milky Way, but in the Large Magellanic Cloud, a satellite galaxy of our own, is one of the largest and most luminous emission nebulae known. It's so bright that if it were located at the same distance as the Orion Nebula, it would cast shadows on Earth at night. The Tarantula Nebula is a factory of stellar giants. It contains some of the most massive stars known to exist, stars with masses exceeding 100 times that of our Sun. These stellar behemoths burn incredibly hot and bright, pouring out tremendous amounts of ultraviolet radiation, ionizing the surrounding gas on a scale that dwarfs anything in our immediate galactic neighborhood. What's particularly fascinating about emission nebulae is that they're not static. They're dynamic, ever-changing environments, though the changes happen on timescales far longer than a human lifetime. Stellar winds from young stars create expanding bubbles in the gas. Radiation pressure carves out cavities. Shock waves from supernovae ripple through the clouds, compressing the gas, potentially triggering new waves of star formation. The gas flows, swirls, eddies. Magnetic fields thread through the nebulae, influencing the motion of charged particles, creating invisible structures that we can only detect through careful observation and analysis. The entire nebula is a complex ecosystem, a web of interacting forces and processes, all working together to transform a cloud of simple gas into a multitude of stars. And when we observe these nebulae, when we capture their light with our telescopes and cameras, we're seeing history. The light from the Orion Nebula that reaches our eyes tonight left that nebula 1,344 years ago. We're seeing the nebula not as it is now, but as it was in the 7th century, when the Tang dynasty ruled China and the Islamic Golden Age was just beginning. The stars we see forming in that nebula might already be fully formed now, in the nebula's present, or they might have failed to form, their gas dispersed by some event we won't see for centuries yet. We're looking into the past, always when we look at the stars. But that doesn't diminish the wonder. If anything, it enhances it. We're not just seeing beauty, we're seeing history. We're witnessing events that happened long before we were born. Light that has traveled across the vast emptiness of space just to reach our eyes, our telescopes, our cameras. Emission nebulae are beacons in the darkness. They're signposts marking the locations of stellar birth throughout our galaxy. They're laboratories where we can study the processes that create stars, planets, and ultimately, the conditions for life. They're works of art, painted by the universe itself, in colors and on scales that challenge our imagination. And they're reminders that the universe is not a cold, dead place. It's active. It's creative. It's constantly bringing new things into existence, even as old things fade away. Somewhere in the Milky Way tonight, in an Emission nebula we may have never observed, a star is being born. It's gathering mass from the surrounding cloud. It's growing warmer, denser, more compact. And one day, perhaps millions of years from now, it will ignite. Nuclear fusion will begin, and it will pour its light out into the nebula that created it, causing that gas to glow, to shine, to become visible across the galaxy. The cycle continues, always, endlessly, beautifully. Rest now in the glow of these stellar nurseries. Let their patient creativity remind you that all things take time. That beauty emerges slowly. That creation is a gradual, gentle process, measured not in days or years, but in eons. The Emission nebulae shine on, indifferent to our small concerns, magnificent in their cosmic purpose. Not all nebulae create their own light. Some are more subtle, more gentle in their illumination. These are the reflection nebulae, clouds of dust and gas that shine not from their own energy, but by reflecting the light of nearby stars. Imagine standing in a darkened room. Someone across the room shines a flashlight, but not directly at you. Instead, the beam illuminates particles of dust floating in the air, and those particles scatter the light in all directions. Some of that scattered light reaches your eyes, and you see the beam, made visible by the dust it illuminates. This is, in essence, what happens with reflection nebulae. Stars shine their light into clouds of dust, and that dust scatters the starlight, making the cloud visible from Earth, even though the cloud itself isn't generating any light. But there's something particularly beautiful about how this scattering works. It doesn't scatter all colors of light equally. Blue light, with its shorter wavelength, scatters more easily than red light. This is the same phenomenon that makes our sky blue during the day. Sunlight enters Earth's atmosphere, and the blue wavelengths scatter more than the other colors, filling the sky with that familiar azure glow. In reflection nebulae, the same principle applies. The dust particles are just the right size to preferentially scatter blue light from nearby stars. The result is that reflection nebulae often appear blue in photographs, a cool, serene blue that contrasts beautifully with the warm reds of Emission nebulae. Of course, not all reflection nebulae are blue. The color depends on several factors: the color of the illuminating star, the size and composition of the dust particles, and the geometry of the situation. But blue is common, and it's become almost a signature of reflection nebulae. One of the most stunning examples of a reflection nebula surrounds the Pleiades star cluster, also known as the Seven Sisters. If you've ever looked up at the night sky in winter and noticed a small, tight grouping of stars that almost looks like a tiny dipper, you've seen the Pleiades. To the naked eye, most people can see 6 or 7 stars in the cluster. Through binoculars or a telescope, dozens more become visible. The Pleiades is a young star cluster, only about 100 million years old. Its stars are hot and blue, still in the early stages of their lifetimes. And surrounding these stars is a faint nebulosity, a reflection nebula that appears in long-exposure photographs as delicate wisps and veils of blue light threading between the stars. For many years, astronomers thought this nebula was the remnant of the cloud from which the Pleiades formed. It would make sense, after all. Stars form from clouds of gas and dust, and some of that material might remain, illuminated by the very stars it helped create. But that's not what's happening here. Studies have shown that the Pleiades is actually passing through a dusty region of space. The nebula we see isn't leftover material from the cluster's formation. It's an unrelated cloud that the cluster happens to be moving through right now. In cosmic terms, this is a chance encounter, a temporary situation. In a few million years, the Pleiades will have moved on, and the reflection nebula will fade from view. But for now, from our perspective, at this moment in cosmic history, the view is spectacular. The blue nebulosity wraps around the brightest stars of the cluster, creating halos and streamers, adding depth and texture to what would otherwise be just points of light. Another famous reflection nebula is the Witch Head Nebula, officially cataloged as IC 2118. This nebula is located about 900 light-years away, and it's illuminated by the bright star Rigel, the blue supergiant that marks Orion's foot. The nebula spans about 50 light-years and has a shape that, with some imagination, resembles the profile of a witch's face. The Witch Head Nebula is composed primarily of dust, and that dust reflects the blue light from Rigel, creating the characteristic color. But what makes this nebula particularly interesting is its association with Rigel itself. Rigel is one of the most luminous stars visible from Earth, a blue supergiant burning through its fuel at a prodigious rate. It's estimated to be only about 10 million years old, incredibly young for a star, but because of its massive size, it's already in a later stage of its evolution than our 4.6 billion-year-old Sun. The light from Rigel is so intense that it can illuminate clouds of dust across dozens of light-years of space. The Witch Head Nebula, despite being several degrees away from Rigel in our sky, is still bright enough to be captured in photographs by amateur astronomers with modest equipment. Reflection nebulae often appear in combination with other types of nebulae. A single cloud of gas and dust might have regions that glow as an emission nebula, energized by ultraviolet light from hot stars, while other parts of the same cloud appear as a reflection nebula, too far from the hottest stars to be ionized, but still close enough to reflect their visible light. The Trifid Nebula, cataloged as Messier 20, is a perfect example of this combination. Located about 5,200 light-years away in the constellation Sagittarius, the Trifid is divided by dark lanes of dust into 3 distinct lobes, which is how it gets its name. The central part of the nebula glows red as an emission nebula, ionized by a massive young star at its core. But surrounding this red region is a blue reflection nebula, illuminated by the same star, but not energized enough to emit its own light. In photographs, the contrast is striking. The warm red of the emission nebula sits adjacent to the cool blue of the reflection nebula, with dark dust lanes threading between them. It's a reminder that nebulae aren't simple, uniform structures. They're complex, with different regions behaving in different ways depending on their distance from illuminating stars, their density, their composition. The dust that makes up reflection nebulae is fascinating in its own right. These aren't large particles. We're talking about grains smaller than the particles in cigarette smoke, tiny motes of carbon, silicon, iron, and other elements, each grain coated with a layer of ice composed of water, methane, and other frozen molecules. These dust grains formed in the outer atmospheres of old, cool stars and were expelled into space by stellar winds. They drifted through the galaxy, accumulated in clouds, and now serve this new purpose, scattering starlight, making nebulae visible, and eventually, perhaps, becoming incorporated into new planets around new stars. In fact, dust like this, dust from reflection nebulae and other sources, was present in the cloud that formed our solar system. Some of it was incorporated into Earth, and some of those ancient dust grains that formed in other stars billions of years ago, have been found in meteorites that have fallen to Earth. We can hold them in our hands, these travelers from distant places and ancient times, preserved in stone, waiting to tell their story. Reflection nebulae tend to be fainter than emission nebulae. They require darker skies and more sensitive equipment to observe and photograph. An emission nebula generates its own light, pumping out photons continuously as hydrogen recombines. A reflection Nebula merely redirects light that's already there, and much of that light scatters in directions away from Earth, never reaching our eyes or telescopes. But this faintness has its own appeal. Reflection nebulae feel delicate, ephemeral, like whispers compared to the shouts of Emission nebulae. They remind us that not everything in the universe announces itself boldly. Some wonders require patience, require us to look carefully, to wait for our eyes to adapt, to take the time necessary to perceive what's hidden in the darkness. There's something meditative about observing or photographing reflection nebulae. The long exposures required, sometimes hours of collected light, teach patience. The faint signals require careful processing, attention to detail, a willingness to tease out subtle features from the noise. It's a practice in looking deeply, in not settling for the obvious, in discovering beauty that doesn't immediately present itself. And when that beauty finally reveals itself, when the blue wisps and streamers appear in the image, there's a sense of reward, of having earned the view through patience and care. The young stars that illuminate reflection nebulae are often obscured by the very dust they're illuminating. We see the effect of their light, the scattered glow, but the stars themselves might be hidden, buried in cocoons of dust. Infrared observations can penetrate this dust, revealing the stars within, but in visible light, we see only the consequences of their presence, the nebulae they make visible. This creates an interesting situation. We're seeing light from stars we can't directly observe, scatter by dust, forming shapes and structures that tell us about invisible sources. It's astronomy through inference, through understanding how light interacts with matter, through knowing what must be there even when we can't see it directly. In some ways, all of astronomy is like this. We're always working with incomplete information, always inferring, always building models of things we can never touch, places we can never visit. We gather light that has traveled for years or centuries or millennia, and from that ancient light, we reconstruct reality. Reflection nebulae are beautiful examples of this process. They're evidence of stars we might not otherwise detect. They're markers of dusty regions in space. They're laboratories for understanding how light and matter interact. And they're works of art, cosmic sculptures shaped by the interplay of starlight and dust. As you drift off tonight, think about those dust grains, those tiny particles floating in space, each one catching and scattering starlight. Think about how something so small, so seemingly insignificant, can create something so beautiful when multiplied across light years. Think about how the universe uses simple principles, repeated on vast scales, to create endless variety and wonder. The reflection nebulae shine their borrowed light across the darkness, patient and serene, waiting for someone to notice, to appreciate, to marvel at their subtle beauty. And we do. We notice. We appreciate. We marvel. In the depths of space, there are places where the stars disappear, regions where the familiar backdrop of distant suns is blocked, obscured, hidden from view. These are the dark nebulae, clouds so dense with dust that they absorb the light from stars behind them, creating silhouettes against the glowing canvas of the Milky Way. Dark nebulae don't shine. They don't emit light. They don't reflect light. They do the opposite. They swallow light, hiding what lies beyond them, creating voids in our view of the galaxy. But these voids aren't empty. Far from it. Dark nebulae are among the densest concentrations of matter in interstellar space. They're clouds of molecular hydrogen and dust, packed so tightly that starlight cannot penetrate them. And within their lightless depths, hidden from direct observation, stars are being born. The most famous dark nebula is probably the Horsehead Nebula, located in the constellation Orion. Rising from a shelf of glowing hydrogen gas, the Horsehead is a column of dark dust, shaped by cosmic coincidence into a form that resembles the head and neck of a horse. It's silhouetted against the red emission nebula IC 434, creating one of the most recognizable shapes in astronomical photography. The Horsehead Nebula is relatively small, only about 3.5 light-years from the top of the head to the bottom of the neck. But what it lacks in size, it makes up for in density. The dust within the Horsehead is so thick that it blocks virtually all visible light from the nebula behind it. Where IC 434 glows bright red, energized by nearby stars, the Horsehead appears as absolute darkness, a cutout in the cosmic tapestry. But this darkness is deceptive. Look at the Horsehead in infrared wavelengths, which can penetrate dust more easily than visible light, and you'll see a different story. The interior of the nebula is revealed, showing structures, filaments, and even young stars hidden within the cloud. The darkness we perceive is simply a limitation of our eyes, our telescopes, the specific wavelengths we happen to observe in. The Horsehead is also slowly evaporating. The same radiation that causes IC 434 to glow is also eroding the Horsehead, wearing it away particle by particle. The distinctive shape we see today won't last forever. In about 5 million years, the Horsehead will have lost enough material that its characteristic profile will no longer be recognizable. It will be gone, dispersed into space. Its brief time as an iconic celestial landmark ended. Another remarkable dark nebula is the Coal Sack, visible from the southern hemisphere. The Coal Sack appears as a dark patch near the Southern Cross, a region where the background stars of the Milky Way suddenly disappear. Indigenous Australian cultures have known about the Coal Sack for thousands of years, incorporating it into their stories and cosmology as part of the Emu in the sky, a dark constellation formed by dust clouds rather than stars. The Coal Sack is one of the closest dark nebulae to Earth, only about 600 light-years away. It spans roughly 7 degrees across the sky, which translates to an actual size of about 60 light-years. Within its dark expanse, molecules are forming, dust is accumulating, and the conditions for star formation are slowly developing. Dark nebulae come in many shapes and sizes. Some are small, isolated clouds called Bok globules, dense knots of dust and gas, typically less than a light-year across. These globules were named after astronomer Bart Bok, who first proposed in the 1940s that they were sites of star formation. He was right. Modern observations have confirmed that many Bok globules contain young stellar objects, protostars in the earliest stages of their development. Bok globules appear as dark spots against brighter backgrounds, looking almost like holes punched in the fabric of space. But they're not holes. They're concentrations. They're places where matter has accumulated, where gravity is pulling material together, where the process of starbirth is beginning. Then there are the larger dark nebulae, vast regions of obscuration that can span dozens or even hundreds of light-years. The Great Rift, also called the Dark Rift, is a series of overlapping dark nebulae that appears to split the Milky Way in two when viewed from a dark site on a clear night. This dark lane runs from the constellation Cygnus down through Aquila and Sagittarius, blocking our view of the galactic center and beyond. The Great Rift isn't a single structure. It's a collection of many dark clouds at various distances from Earth, all happening to lie roughly along our line of sight to the center of the galaxy. Some of these clouds are only a few hundred light-years away. Others are thousands of light-years distant. Together, they create the illusion of a great division in the Milky Way, a dark river flowing through the stars. Ancient cultures saw this dark lane and incorporated it into their mythologies. Some saw it as a road, a path that souls traveled after death. Others saw it as a serpent, a cosmic river, or a gap between worlds. They didn't know what caused the darkness, but they recognized it as significant, as something that demanded explanation and meaning. What makes dark nebulae particularly fascinating is what they hide. Behind and within these clouds of dust, there are countless stars we cannot see in visible light. If we could somehow remove all the dust from the galaxy, if we could clear away the dark nebulae, the night sky would be dramatically different. We would see more stars, fainter stars, stars that are currently hidden from view. The Milky Way would appear brighter, more continuous, less divided by dark lanes and patches. But we cannot remove the dust, and in many ways, we wouldn't want to. Because within that dust, within those dark nebulae, the future of the galaxy is being shaped. Stars are forming. Planetary systems are beginning. The next generation of stellar objects is gestating in darkness, protected from harsh radiation, slowly accumulating mass. The dust in dark nebulae serves another crucial purpose. It facilitates the formation of molecules. In the vast emptiness of interstellar space, atoms rarely collide. The density is too low. But on the surfaces of dust grains, atoms can accumulate, meet, and bond together, forming molecules. Water ice forms on dust grains. Carbon monoxide, ammonia, methanol, and even more complex organic molecules can be found in dark nebulae. Some of the molecules discovered in these clouds are the same molecules that are essential for life as we know it. Amino acids, the building blocks of proteins, have been found in meteorites that originated from clouds like these. This raises a profound possibility that the chemistry of life began not on Earth, but in the dark nebulae where our solar system formed. That the molecules necessary for life were already present in the cloud that collapsed to form the sun and planets. That we're not just made of stardust, but of the specific chemistry that occurs in these dark, cold, molecular clouds. Observing dark nebulae requires a different approach than observing emission or reflection nebulae. You can't point your telescope at a dark nebula and expect to see much. They're defined by absence, by what's not there. Instead, you need context. You need bright nebulae behind them, or rich star fields, something that the dark nebula can block, creating contrast. The best views of dark nebulae often come from wide-field observations, images that capture large sections of the sky, showing how the dark clouds are positioned relative to brighter regions. In these images, the dark nebulae reveal their shapes, their extent, their relationships to nearby stars and emission nebulae. Some dark nebulae have wonderfully evocative names. The Pipe Nebula, in Ophiuchus, resembles a tobacco pipe in silhouette. The Snake Nebula appears as a dark, sinuous band against the bright star clouds of Sagittarius. The Cone Nebula, part of the larger NGC 2264 region, is a dark pillar of dust 7 light-years long, pointing directly toward the star cluster that's illuminating it. Each of these nebulae has its own structure, its own history, its own future. The Cone Nebula, like the Horsehead, is being eroded by radiation from nearby stars. But it's also a site of active star formation. Within the cone, protected from the most intense radiation by the surrounding dust, stars are growing, preparing to emerge and join the cluster that will eventually destroy their nursery. It's a pattern that repeats throughout the galaxy. Dark nebulae serve as stellar nurseries, protecting forming stars from external radiation. But as those stars mature, as they begin to shine, they turn on their birthplace. Their light, their stellar winds, their radiation begins to erode and disperse the very cloud that sheltered them. Eventually, the dark nebula is destroyed, scattered back into the interstellar medium. The stars that formed within it emerge into the light, freed from their dusty cocoons. The nebula that was once dark and dense becomes thin and transparent, and the material that composed it drifts away, perhaps to accumulate somewhere else, to form a new dark nebula, to begin the cycle again. The timescales involved are immense. A dark nebula might exist for tens of millions of years before producing stars. Those stars might take millions more years to mature enough to begin dispersing their birthplace. And then the dispersal itself might take millions of years. From our perspective, dark nebulae appear eternal, unchanging, but they're temporary, just like everything else in the universe. There's something humbling about dark nebulae. They remind us that much of the universe is hidden from us, that what we see is only a fraction of what exists. That darkness doesn't mean emptiness, and that absence of light doesn't mean absence of matter or activity or importance. They also remind us that creation often happens in darkness, in hidden places, away from observation. Stars form in the depths of dark nebulae, shielded from view. It's only later, after they've grown strong enough, that they emerge into the light and make themselves known. Perhaps there's a lesson there, that important things often develop out of sight, that patience is required, that not everything needs to be visible to be valuable. As you rest tonight, think about those dark clouds floating in space. Think about the stars forming within them, slowly, patiently, in absolute darkness. Think about how they'll eventually emerge, bringing their light into the galaxy, contributing their energy and elements to the cosmic cycle. And think about how darkness and light are partners, not opposites, how each defines the other, how both are necessary for the universe to function, to create, to evolve. The dark nebulae drift silently through the galaxy, invisible to casual observation, but crucial to the story of stellar birth. They hide much. They reveal much. They teach us that not everything important shines. Despite their name, planetary nebulae have nothing to do with planets. They're the final breath of dying stars, glowing monuments to stellar death, beautiful and ephemeral shells of gas expelled into space when stars like our Sun reach the end of their lives. The name is a historical accident. When astronomers first observed these objects through early telescopes, they appeared as small, round, disc-like shapes reminiscent of planets. The name stuck, even after we learned what they truly were. Now we know. Planetary nebulae are the dying gasps of stars, their outer layers cast off into space, illuminated by the hot stellar core left behind. Our Sun will create a planetary nebula one day. Not soon, not for billions of years, but eventually. When the Sun exhausts the hydrogen fuel in its core, it will begin to change. It will swell, becoming a red giant, expanding outward until it potentially engulfs the inner planets. Mercury will almost certainly be consumed. Venus likely as well. Earth's fate is less certain, but even if our planet survives, it will be a scorched, lifeless rock, its oceans boiled away, its atmosphere stripped. For millions of years, the Sun will exist in this red giant phase, burning helium in its core, pulsating, unstable. And then, in a series of pulses, it will begin to shed its outer layers. Not violently, not in an explosion, but gently, relatively speaking. Shells of gas will drift away from the core, expanding into space at speeds of tens of kilometers per second. And at the center, the core will be exposed. No longer hidden beneath layers of stellar atmosphere. The core will shine directly into space. It will be incredibly hot, perhaps 100,000 degrees Celsius or more, and it will pour out ultraviolet radiation. This ultraviolet light will ionize the expanding shells of gas, causing them to glow, creating a planetary nebula. This is the fate of all stars with masses between about 1/2 and 8 times the mass of the Sun. It's the destiny of the vast majority of stars in our galaxy. They live for billions of years, shining steadily, and then, in their final stages, they create these beautiful structures, these glowing shells that last for perhaps 10,000 to 20,000 years before fading into invisibility. One of the most famous planetary nebulae is the Ring Nebula, catalogued as Messier 57. Located about 2,300 light-years away in the constellation Lyra, the Ring Nebula appears as a ghostly smoke ring in the sky, a perfect circle of glowing gas surrounding a faint central star. But the Ring Nebula isn't actually a ring. It's a cylinder or barrel of gas, and we're looking at it nearly end-on. The appearance of a ring is a projection effect. The gas is thicker along the edges of the cylinder from our perspective, so that's where it appears brightest. The center looks dimmer because we're looking through less material there. This three-dimensional structure is common among planetary nebulae, though it wasn't always understood. For a long time, astronomers debated the true shapes of these objects. Were they spherical shells, disks, rings? It took careful observation and modeling to realize that what we see depends heavily on our viewing angle, and that many planetary nebulae have complex, three-dimensional structures. The Ring Nebula is expanding. The gas is moving outward at about 20 to 30 kilometers per second. Not fast by cosmic standards, but fast enough that over thousands of years, the nebula grows noticeably larger. Eventually, it will expand so much that it becomes too diffuse to see, its material spreading out and mixing with the general interstellar medium. Another spectacular planetary nebula is the Cat's Eye Nebula, designated NGC 6543. This nebula is extraordinarily complex, with multiple shells, jets, and structures that have puzzled astronomers for decades. Long-exposure images reveal at least 11 concentric shells of gas, suggesting that the central star expelled material in multiple episodes, perhaps over thousands of years. The Cat's Eye also shows evidence of a binary companion. Many planetary nebulae have shapes that can't be explained by a single star. They're too asymmetric, too complex. But if the dying star has a companion, perhaps a smaller star in orbit around it, that companion's gravity can influence how the gas is expelled, creating lobes, jets, and other non-spherical structures. The shapes of planetary nebulae are incredibly diverse. Some, like the Ring Nebula, appear relatively simple and symmetric. Others are fantastically complex. The Butterfly Nebula, or NGC 6302, has two lobes extending in opposite directions from central star, resembling the wings of an insect. The central star is hidden by a thick dust lane, but the lobes themselves glow brilliantly, containing some of the hottest gas found in any planetary nebula. The Helix Nebula, cataloged as NGC 7293, is one of the closest planetary nebulae to Earth, only about 700 light-years away. It's also one of the largest in apparent size, spanning nearly half a degree across the sky, roughly the same angular size as the full moon. This makes it a popular target for amateur astronomers, though its large size and relatively low surface brightness mean it's often described as challenging to observe visually. The Helix has a remarkably detailed structure. High-resolution images reveal thousands of radial streaks, cometary knots of denser gas, each one pointing away from the central star. These knots are fascinating objects. They're larger than our entire solar system, and they're being photoevaporated by the intense ultraviolet radiation from the central star, each one creating a tiny tail as material is stripped away. Planetary nebulae come in a bewildering variety of shapes. There are bipolar nebulae with two lobes, point-symmetric nebulae with spiraling structures, irregular nebulae with chaotic, complex forms, and relatively simple spherical nebulae. Astronomers have classification schemes to categorize these shapes, but the underlying causes of this diversity are still not fully understood. What's clear is that the death of a star is not a simple process. It's not just a matter of the outer layers drifting away evenly in all directions. Instead, factors like rotation, magnetic fields, stellar pulsations, and the presence of companion stars all play roles in shaping how the gas is expelled and how the resulting nebula appears. The central stars of planetary nebulae are among the hottest stars known. Stripped of their outer layers, these white dwarf precursors have surface temperatures that can exceed 100,000 degrees Celsius, 10 times hotter than the Sun's surface. They're incredibly luminous in ultraviolet wavelengths, though relatively faint in visible light because they're so small, often no larger than Earth. These hot cores are the future of our Sun. After the Sun creates its planetary nebula, after it sheds its outer layers, what remains will be a white dwarf. This white dwarf will contain about half the Sun's current mass, compressed into a volume roughly the size of Earth. It will shine not from nuclear fusion, which will have ceased, but from residual heat, gradually cooling over billions of years. White dwarfs are incredibly dense. A teaspoon of white dwarf material would weigh several tons on Earth. The matter exists in a state unknown anywhere on our planet, held up against further collapse by quantum mechanical pressure from electrons. It's matter at the edge of what's physically possible. Planetary nebulae are relatively rare in the sky. Only a few thousand are known in our galaxy, though there must be many more hidden by dust or simply too faint to detect. This rarity is due to their brief lifetimes. While the stars that create them live for billions of years, the nebulae themselves last only tens of thousands of years, a blink of an eye in cosmic terms. But in that brief window, they're spectacular. They're among the most beautiful objects in the universe, their colors ranging from reds and greens to blues and purples, depending on which elements are present and being ionized. Hydrogen gives reds. Oxygen gives greens and teals. Nitrogen contributes reds and oranges. Together, these elements create nebulae that look almost artificially colored, too vibrant to be real, yet entirely natural. The study of planetary nebulae teaches us about stellar evolution. By observing thousands of these objects at different stages of their existence, astronomers can piece together the sequence of events that occurs when a sun-like star dies. We can see newly formed nebulae, still compact and dense. We can see middle-aged nebulae in full bloom. And we can see old nebulae beginning to fade, their gas dispersing, their central stars dimming. From these observations, we learn what awaits our own Sunday. We learn the timeline of its death. We learn what the solar system will look like in 7 or 8 billion years, when the sun swells into a red giant and then sheds its outer layers. We get a preview of the end, seen in objects thousands of light years away. But planetary nebulae aren't just endpoints. They're also contributors. The gas they release back into the interstellar medium is enriched with elements created during the star's lifetime. Carbon, nitrogen, oxygen, and other elements synthesized in the star's interior are now mixing with the general galactic environment. This enriched gas will eventually become part of new nebulae, new stars, new planets. In this way, planetary nebulae are part of the great cosmic recycling program. The elements that compose our bodies, our planet, everything we see around us, have cycled through multiple generations of stars. Some of those elements were expelled in planetary nebulae billions of years ago. Stars died, released their material, and that material became part of the cloud that formed our solar system. We are connected to planetary nebulae in the most literal sense. We are made of their substance. We are the descendants of their chemistry. And one day, far in the future, the sun will create its own planetary nebula, returning its material to space, contributing to yet another generation of cosmic recycling. There's a gentle quality to planetary nebulae, especially compared to the violent deaths of massive stars and supernovae. This is a quiet passing, a peaceful release. The star doesn't explode. It simply lets go, allowing its outer layers to drift away, revealing the core that has sustained it for billions of years. In many cultures, the end of life is seen as a transition, not an ending. Planetary nebulae embody this idea beautifully. The star doesn't cease to exist. It transforms. It becomes something new, something smaller and denser and different. And in that transformation, it creates beauty, a luminous shell that will shine for thousands of years before fading. As you drift towards sleep tonight, think about those glowing shells, those monuments to stellar death, floating in the darkness of space. Think about the stars at their centers, stripped bare, cooling slowly, their fusion fires extinguished. Think about how endings can be beautiful, how transformation is natural, how what we leave behind can shine long after we're gone. The planetary nebulae glow softly in the night, temporary and precious, reminders that even death can create wonder. Not all stars die gently. Some end their lives in spectacular violence, in explosions so powerful that for a brief time, a single star can outshine an entire galaxy. These are supernovae, the catastrophic deaths of massive stars, and the nebulae they leave behind are among the most dynamic and energetic objects in the universe. A supernova remnant is what remains after the explosion. It's an expanding shell of gas and dust, heated to millions of degrees, racing outward at thousands of kilometers per second, carrying with it the elements forged in the star's core and in the explosion itself. These aren't the peaceful nebulae of dying sun-like stars. These are violent, chaotic, turbulent structures, shaped by shock waves and magnetic fields, glowing not just from ionization, but from the sheer energy of the explosion that created them. The most famous supernova remnant is probably the Crab Nebula, designated Messier 1. It's located about 6,500 light-years away in the constellation Taurus, and it's the remains of a supernova that exploded in the year 1054. That explosion was witnessed by astronomers in China, Japan, and the Middle East, who recorded the appearance of a brilliant new star in the sky, one bright enough to be visible during the day for several weeks. Nearly 1,000 years later, we can still see the results of that explosion. The Crab Nebula is a complex, filamentary structure about 11 light-years across, still expanding at roughly 1,500 kilometers per second. It's one of the most studied objects in astronomy, observed at every wavelength from radio waves to gamma rays. At the heart of the Crab Nebula is something extraordinary, a pulsar. This is the collapsed core of the original star, compressed into a sphere only about 20 kilometers across, but containing more mass than our Sun. It spins 30 times per second, and as it spins, it emits beams of radiation from its magnetic poles. When those beams sweep past Earth, we detect pulses of light and radio waves, like a cosmic lighthouse. This pulsar is the engine that powers the nebula. It pumps energy into the surrounding gas, creating a wind of high-energy particles that flow outward, creating structures and patterns in the nebula. Without the pulsar, the Crab Nebula would be cooling and fading. Instead, it remains active, dynamic, constantly changing on timescales short enough that we can actually observe the changes over months and years. Another remarkable supernova remnant is the Veil Nebula, part of the larger Cygnus Loop. This remnant is much older than the Crab Nebula, perhaps 10,000 to 20,000 years old. The original supernova occurred long before recorded human history, and the expanding shell has grown to enormous size, spanning several degrees across the sky. The Veil Nebula appears as delicate, wispy filaments of glowing gas, colored in shades of red, green, and blue. These colors come from different elements. Hydrogen emits red light, oxygen creates green and teal hues, and sulfur adds deeper reds. The filaments trace out the edges of the expanding shockwave, regions where the rapidly moving gas collides with the stationary interstellar medium, heating it and causing it to glow. What's particularly beautiful about the Veil Nebula is its structure. The filaments are incredibly thin, complex, and detailed, looking almost like cosmic lace stretched across the sky. They reveal the turbulent nature of the expansion, the way the shock wave is sculpted by variations in the density of the surrounding space, by magnetic fields, by the complex physics of supersonic flows. The veil is expanding at about 600,000 kilometers per hour, though that's actually slowing down. When the supernova first exploded, the material would have been moving much faster. Over thousands of years, interaction with the interstellar medium has been gradually decelerating the expansion. Eventually, in tens of thousands of years more, the expansion will slow to the point where the remnant merges with the general background gas and becomes indistinguishable from it. Cassiopeia A is another famous supernova remnant, one of the youngest known. The supernova that created it exploded only about 340 years ago, around 1680, though, curiously, there are no reliable historical records of the event. It should have been visible from Earth, perhaps as bright as the planet Venus, but no one seems to have recorded it. Either it was obscured by dust, or the records have been lost, or perhaps the explosion occurred during a time when no one was watching that particular part of the sky. Cassiopeia A is a chaotic, complex remnant. High-resolution images reveal thousands of individual knots and filaments of gas, each one racing outward at its own velocity, creating a three-dimensional structure of incredible complexity. The remnant is also a strong source of radio waves and X-rays, making it one of the brightest objects in the sky at those wavelengths despite being relatively faint in visible light. At the center of Cassiopeia A is a neutron star, the collapsed core of the original star. This neutron star is young and hot, still cooling from its violent birth, and it contributes to the overall energy output of the remnant. Observations suggest that this neutron star might have a surface of carbon, essentially a diamond coating on a ball of impossibly dense matter. Supernova remnants come in different types, depending on the nature of the original explosion. Some, like the Crab Nebula, are the results of core collapse supernovae, where massive stars exhaust their fuel and their cores collapse catastrophically. Others, like the remnant of Tycho's supernova from 1572, are the results of type I supernovae, thermonuclear explosions of white dwarf stars. Type I supernovae occur in binary systems where a white dwarf is pulling matter from a companion star. As the white dwarf accumulates mass, it eventually reaches a critical limit, about 1.4 times the mass of the Sun. At this point, the quantum pressure that was holding up the white dwarf can no longer support the weight, and the star collapses. The collapse triggers runaway nuclear fusion, and the entire star explodes, leaving no remnant core behind, just an expanding shell of gas. These type I supernovae are remarkably consistent in their brightness, which makes them useful as cosmic distance markers. Astronomers use them to measure distances to far galaxies, and it was observations of distant type I supernovae that led to the discovery that the universe's expansion is accelerating, a finding that earned the Nobel Prize and introduced us to the concept of dark energy. The elements created in supernovae are crucial to the universe as we know it. During a star's normal lifetime, fusion creates elements up to iron. But creating elements heavier than iron requires energy input rather than releasing energy. So these elements don't form during normal stellar fusion. They're created in the intense conditions of a supernova explosion. Gold, silver, platinum, uranium, and all the other elements heavier than iron were forged in supernovae. The gold in jewelry, the uranium in nuclear reactors, the silver in electronics, all of it came from exploding stars. These elements were blasted into space by supernovae, mixed with the interstellar medium, and eventually incorporated into new stars and planets. Earth itself is enriched with supernova products. The heavy elements in our planet's core, in its crust, in our bodies, all trace back to ancient supernovae that exploded billions of years ago, long before a solar system existed. We are, quite literally, made of star explosions. Supernova remnants also play a crucial role in shaping the galaxy. The shock waves from these explosions compress nearby clouds of gas, potentially triggering new episodes of star formation. The energy they inject into the interstellar medium creates turbulence, drives galactic fountains, and helps regulate the rate at which stars form in galaxies. Some supernova remnants interact with nearby nebulae in spectacular ways. The shock wave from a supernova can slam into a nearby molecular cloud, compressing it, heating it, creating new structures. We see examples of this throughout the galaxy, regions where a supernova remnant is colliding with a dark nebula or an emission nebula, creating a complex interplay of old and new, destruction and creation. The lifetimes of supernova remnants vary depending on their environment. In regions of low-density interstellar gas, a remnant can expand for tens of thousands of years, growing to enormous size before finally merging with the background. In denser regions, the expansion is slowed more quickly, and the remnant might fade in just a few thousand years. But while they last, supernova remnants are spectacular laboratories for physics. They contain some of the hottest, most energetic matter in the universe. They accelerate particles to relativistic speeds, creating cosmic rays. They compress and amplify magnetic fields. They drive shock waves through the interstellar medium. All of these processes can be studied in supernova remnants, giving us insights into extreme physics that we can't replicate on Earth. The shape of a supernova remnant evolves over time. Initially, shortly after the explosion, the remnant is relatively small and dense, expanding rapidly. This is called a free expansion phase. The ejected material is moving so fast that it encounters relatively little resistance from the surrounding interstellar medium. As time passes, the remnant sweeps up more and more of the surrounding gas. Eventually, the mass of swept-up material becomes comparable to the mass of the ejected material. At this point, the expansion begins to slow noticeably. This is the Sedov-Taylor phase, and it's when the remnant often develops its characteristic shell-like appearance, with a bright rim where the shock wave is compressing and heating the interstellar gas. Finally, after tens of thousands of years, the expansion slows to the point where the shock wave is no longer strong enough to heat the gas to visible temperatures. The remnant fades from view, merging with the general interstellar medium. This is the snowplow phase, the final stage before the remnant becomes indistinguishable from its surroundings. Throughout this evolution, the remnant is constantly changing. Material is flowing, mixing, heating, cooling. Magnetic fields are being wound up and amplified. Particles are being accelerated. It's a dynamic, evolving system, a monument to stellar death that gradually transforms and fades over cosmic timescales. There's something profound about observing a supernova remnant. You're looking at the scattered remains of a star, a sun that once shone for millions or billions of years, that perhaps had planets that contributed light to some distant sky. And now it's gone, destroyed in an instant of cosmic violence. Its matter spread across light years of space. But that destruction enabled creation. The heavy elements now drifting through the remnant will one day become part of new stars, new planets. The energy injected by the explosion might trigger the collapse of nearby clouds, initiating new rounds of star formation. Death and birth, destruction and creation, forever intertwined. As you relax tonight, think about those expanding shells of gas, racing through space at unimaginable speeds. Think about the pulsars at their centers, spinning dozens of times per second, the crushed remnants of stellar cores. Think about the elements being carried by those shells, elements that will one day build new worlds. Think about how even the most violent events in the universe serve a purpose. How destruction is part of the cycle. How endings enable new beginnings. The supernova remnants expand through the darkness, glowing monuments to stellar death, proof that even catastrophe can create beauty, and that nothing in the universe is ever truly lost, only transformed. There are places in the galaxy where stars are being born right now, at this very moment. Regions where vast clouds of gas and dust are collapsing under their own gravity, fragmenting into smaller and smaller pieces, each one destined to become a star. These are the stellar nurseries, the maternity wards of the cosmos, and they're among the most active and dynamic regions we can observe. Stellar nurseries exist within giant molecular clouds, enormous concentrations of cold gas and dust that can span hundreds of light years and contain enough material to create thousands or even millions of stars. These clouds are the densest, coldest places in the interstellar medium, with temperatures often just a few degrees above absolute zero. In the darkness and cold of these molecular clouds, hydrogen exists not as individual atoms, but as molecules, two hydrogen atoms bonded together. This molecular hydrogen, along with dust, carbon monoxide, and trace amounts of other molecules, makes up the bulk of the cloud's mass. And within certain regions of these clouds, where the density is highest, where gravity is strong enough to overcome the outward pressure of the gas, star formation begins. The Eagle Nebula, which we touched on earlier when discussing Emission Nebulae, is home to one of the most famous stellar nurseries. The pillars of creation, those towering columns of gas and dust, are sites of active star formation. Within the pillars, hidden from visible light by the surrounding dust, young stars are growing, accreting material from their surroundings, slowly increasing in mass. These forming stars are called protostars. They're not yet hot enough for nuclear fusion to begin in their cores. They're still gathering mass, still growing, powered not by fusion, but by gravitational contraction. As material falls onto a protostar, gravitational potential energy is converted into heat, causing the protostar to glow, mostly in infrared wavelengths that can penetrate the surrounding dust. The process of star formation is slow by human standards, but remarkably fast on cosmic timescales. A protostar might take a few 100,000 years to accumulate enough mass to ignite fusion. That seems like a long time, but remember that the star will then shine for millions or billions of years. The formation period is just a brief prelude to a long stellar lifetime. Not all protostars are created equal. The mass they eventually accumulate depends on the conditions in the cloud where they form. Some protostars will become small, cool red dwarfs, stars with only a fraction of the sun's mass. Others will grow into massive, hot blue giants, stars dozens of times more massive than the sun. The distribution of stellar masses follows a predictable pattern, with small stars being much more common than massive ones. The Orion Nebula, which we discussed when talking about Emission Nebulae, is another spectacular stellar nursery. Located just 1,344 light-years away, it's the closest massive star-forming region to Earth, making it an invaluable laboratory for studying how stars are born. Within the Orion Nebula, infrared observations have revealed hundreds of protostars in various stages of development. Some are still deeply embedded in their dusty cocoons, barely visible even in infrared. Others have begun to emerge, dispersing their surrounding material, becoming visible as young stellar objects. And at the center, the trapezium stars, those four bright stars visible even in small telescopes, represent the successful outcome of this process. Massive young stars that have completed their formation and now flood the nebula with their light. Around many of these young stars, we can see disks of material, flattened clouds of gas, and dust rotating around the forming star. These are protoplanetary disks, and they're the birthplaces of planets. The same process that creates stars also creates planetary systems. As the cloud collapses, conservation of angular momentum causes it to flatten into a disk. The star forms at the center of the disk, and planets form from the leftover material in the disk. We've detected thousands of these protoplanetary disks in various stellar nurseries. Some are large and massive, containing more than enough material to create systems like our own solar system. Others are smaller, more modest, perhaps capable of creating only a few small planets. Each disk is unique, shaped by the specific conditions in which it formed, by the mass of the central star, by interactions with nearby, forming stars. The process of planet formation is still not completely understood, but observations of protoplanetary disks have revealed many of the key stages. We see disks with gaps and rings, likely carved by forming planets. We see disks that are transitional, showing signs that planets have already formed and are clearing away the remaining gas. And we see mature planetary systems around young stars, confirmation that the process works, that stars and planets form together. One of the challenges of observing stellar nurseries is that they're shrouded in dust. The same material that's collapsing to form stars also blocks visible light, making it difficult or impossible to see what's happening inside. This is why infrared astronomy has been so crucial to understanding star formation. Infrared wavelengths can penetrate dust much more effectively than visible light, allowing us to peer inside molecular clouds and see the protostars within. The Spitzer Space Telescope, which operated from 2003 to 2020, revolutionized our understanding of stellar nurseries by observing them in infrared wavelengths. It revealed protostars that had never been seen before, mapped the structures of molecular clouds, and helped us understand how star formation proceeds. The James Webb Space Telescope, with its even more powerful infrared capabilities, is now continuing this work, providing unprecedented views of stellar nurseries both in our galaxy and in distant galaxies. Stellar nurseries are not calm, peaceful places. They're dynamic, turbulent, full of activity. Protostars don't just quietly accrete material. They launch jets and outflows, high-speed streams of gas that shoot out from their poles at hundreds of kilometers per second. These jets plow into the surrounding cloud, creating shock waves, compressing gas, potentially triggering the formation of more stars. The jets are powered by the accretion process itself. As material falls onto the protostar through the protoplanetary disk, it doesn't all end up in the star. Some of it is redirected along magnetic field lines and expelled from the poles at high velocity. These bipolar outflows are a characteristic feature of star formation, visible in nearly every stellar nursery we observe. When these jets slam into the surrounding cloud, they create objects called Herbig-Haro objects, glowing knots and filaments of shock-heated gas. Herbig-Haro objects are often among the most visually striking features in stellar nurseries, appearing as bright patches or jets extending from invisible protostars. They're temporary structures, lasting only a few thousand years before fading, but they're important diagnostics of the star formation process. The rate at which stars form in a molecular cloud depends on many factors. The density of the cloud matters. Denser regions form stars more quickly. The temperature matters. Colder clouds form stars more easily because thermal pressure provides less resistance to gravitational collapse. Turbulence matters. Molecular clouds are turbulent, with gas flowing and swirling in complex patterns, and this turbulence can both aid and hinder star formation. Magnetic fields also play a crucial role. Molecular clouds are threaded with magnetic fields, and these fields provide support against gravitational collapse. For a cloud region to collapse and form stars, gravity must overcome not just thermal pressure and turbulence, but also magnetic pressure. The interplay between gravity, pressure, turbulence, and magnetic fields determines where and when stars will form. Some stellar nurseries form stars in clusters. These are regions where dozens, hundreds, or even thousands of stars form in close proximity, creating bound stellar clusters that will remain together for millions or billions of years. The Pleiades is an example of such a cluster, a group of stars that form together and are still gravitationally bound. Other stellar nurseries form stars in more dispersed associations, loose groupings that will eventually disperse as the stars move apart. Our own Sun likely formed in a stellar nursery alongside hundreds of sibling stars, but those siblings have long since scattered across the galaxy. We might never know which stars were born in the same cloud as the Sun. The process of star formation has a self-regulating quality. As stars form, they begin to affect their environment. Their radiation heats the surrounding gas. Their stellar winds and outflows push material around. If the stars are massive enough, they can ionize large regions of the cloud, creating emission nebulae and preventing further star formation in those regions. Eventually, the most massive stars in a stellar nursery will reach the end of their lives and explode as supernovae. These explosions inject enormous amounts of energy into the remaining cloud, potentially dispersing it entirely and ending star formation in that region. But the same explosions might compress nearby clouds, triggering new episodes of star formation elsewhere. This is how star formation proceeds in the galaxy, not as a continuous, uniform process, but as a series of bursts and lulls, driven by feedback from the stars themselves. Regions of active star formation are scattered throughout the galactic disk, each one representing a molecular cloud in the process of being transformed into stars. The timescales involved mean that we can't watch individual stars form. A human lifetime is far too short to see significant changes in a stellar nursery. But by observing many stellar nurseries at different stages of evolution, we can piece together this sequence of events. We can see what newly formed protostars look like. We can see protostars that are a bit more evolved, beginning to clear their surroundings. We can see young stars that have just completed their formation. And we can see mature stars that have dispersed their birth clouds entirely. From these snapshots, distributed across space and time, we reconstruct the story of stellar birth. It's like watching a time-lapse created not from sequential images of one object, but from simultaneous images of many similar objects at different stages. The universe provides the time-lapse. We just have to know how to interpret it. There's something deeply moving about stellar nurseries. They're places of creation, of beginnings, of potential. Every star that will ever shine is born in a place like this. Every planetary system begins here. Every possible future, every world that might harbor life, every story that will unfold around a star, it all starts in these dark, cold, dusty clouds. And the process is happening constantly. Right now, as you listen to these words, somewhere in the Milky Way, a cloud is collapsing. Gravity is pulling material together. A protostar is forming. In a few 100,000 years, that protostar will ignite, beginning a journey that might last billions of years. The universe is always creating, always beginning, always bringing new lights into existence. As you rest tonight, think about those stellar nurseries, those vast clouds where stars are being born. Think about the protostars within them, slowly gathering mass, growing stronger, moving toward the moment when fusion will ignite in their cores. Think about how every ending is also a beginning, how the material expelled by dying stars becomes the raw material for new stellar nurseries, how the cycle continues, endlessly, beautifully, across the galaxy. The stellar nurseries drift through space, incubators of light, promise made manifest in molecular clouds, the future taking shape in darkness, waiting to shine. Among all the structures we've explored tonight, few have captured the public imagination quite like the pillars of creation. These towering columns of gas and dust, rising from the heart of the Eagle Nebula, have become perhaps the most iconic image in astronomy, instantly recognizable, hauntingly beautiful, and deeply mysterious. The pillars of creation were first brought to widespread attention in 1995, when the Hubble Space Telescope captured a stunning image of them. That photograph showed 3 enormous pillars, each several light-years tall, sculpted by radiation and stellar winds, their surfaces glowing, their interiors dark with dense dust. The image was immediately captivating, appearing on magazine covers, in textbooks, in museums around the world. But what exactly are the pillars of creation? Why do they exist? And what's happening within them? The pillars are part of the Eagle Nebula, a vast star-forming region located about 7,000 light-years away in the constellation Serpens. The entire nebula spans roughly 70 by 55 light-years, a substantial region of space, and it contains enough gas and dust to create thousands of stars. The pillars themselves are part of a larger structure, a dense molecular cloud where active star formation is taking place. The pillars are tall. The largest of the 3 extends approximately 4 light-years from base to tip. To put that in perspective, the distance from our Sun to the nearest star, Proxima Centauri, is about 4.2 light-years. The pillar is nearly as tall as that entire distance. It's an almost incomprehensible scale, a structure so vast that light takes 4 years to travel from its base to its tip. The pillars are made primarily of hydrogen gas and dust. The density varies throughout the structure, but in the densest regions, there might be thousands of hydrogen molecules per cubic centimeter. That's still incredibly sparse by Earth standards. Our atmosphere at sea level contains trillions upon trillions of molecules per cubic centimeter. But in the context of interstellar space, where the average density might be only 1 atom per cubic centimeter, the pillars are remarkably dense. The shape of the pillars is no accident. They're being sculpted by a nearby cluster of young, massive stars. These stars, located just beyond the pillars from our perspective, are incredibly hot and luminous. They pour out intense ultraviolet radiation and powerful stellar winds, and this energy streams into the Eagle Nebula, eroding the molecular cloud, pushing it back, carving it into shapes. The pillars survive because they're denser than their surroundings. Think of them like rocks in a river. The water flows around the rocks, eroding the riverbed, but the rocks themselves resist the flow because they're harder, more solid. Similarly, the pillars resist the onslaught of radiation and stellar wind because they're denser, more massive, more capable of withstanding the pressure. But they're not immortal. They're being eroded, slowly but steadily. The surfaces of the pillars are being photoevaporated, meaning that the ultraviolet radiation is heating the surface gas enough that it can escape the pillar's weak gravity and flow away into space. This creates the glowing edges we see in photographs, the bright rims where the gas is being heated and ionized. At the current rate of erosion, the pillars won't last much longer. Cosmically speaking, estimates suggest they might be completely dispersed within a few tens of thousands of years. That seems like a long time, but remember that the Eagle Nebula itself is several million years old. The pillars are temporary structures, shaped by the current environment, destined to be destroyed by the same forces that make them visible. But even as they're being destroyed, they're creating. Deep within the pillars, shielded from the intense radiation by the surrounding gas and dust, stars are forming. Observations in infrared wavelengths, which can penetrate the dust, have revealed dense knots within the pillars, regions where gravity is winning the battle against pressure, where protostars are growing. These embedded protostars are called evaporating gaseous globules, or EGGs. They appear as finger-like protrusions on the surface of the pillars, small dense clumps that are still thick enough to resist the photoevaporation that's destroying the rest of the pillar. Within these EGGs, stars are gestating, hidden from view, protected by their dusty cocoons. The process is a race. Can the protostar accumulate enough mass to ignite fusion before the surrounding material is completely eroded away? Sometimes yes, sometimes no. Some of the EGs will successfully produce stars. Others will be dispersed before star formation can complete, their material scattered back into the interstellar medium, perhaps to try again somewhere else. This raises a fascinating possibility. The stars forming within the pillars of creation might be the last generation of stars to form from this particular cloud. After they emerge, after they complete their formation, the pillars will likely be gone, eroded away. These stars will be witnesses to their own birthplace's destruction, monuments to a structure that no longer exists. In 2014, the Hubble Space Telescope revisited the pillars of creation, capturing a new, higher-resolution image using more advanced instruments. This new image revealed even finer detail, showing smaller structures, more complex textures, jets and outflows from embedded protostars. It confirmed what the earlier image had suggested, that the pillars are dynamic, active, complex environments, not static monuments, but living laboratories of star formation. The colors in the famous Hubble images are not quite what you would see if you could visit the pillars. The images are composites, combining observations at different wavelengths and assigning colors to represent different elements and processes. Oxygen emissions are shown in blue, sulfur in orange, hydrogen and nitrogen in green. The result is more vivid than reality would be, but also more informative, encoding scientific data into visual form. If you could somehow travel to the Eagle Nebula and approach the pillars of creation, you would see them not as the vibrant green and brown of the Hubble image, but as more subtle shades, perhaps pale reds and blues, dimmer, more ghostly. The human eye isn't sensitive enough to see the faint nebular emissions in full color. But you would see the scale, the impossible vastness of these structures, columns of cloud reaching up into the darkness like frozen waterfalls or cosmic stalagmites. And you would see the stars. The cluster of young, hot stars that's eroding the pillars would be brilliant, their blue-white light flooding the region. Some of these stars are O-type and B-type giants, the most massive and luminous stars that exist. They burn through their fuel quickly, living for only a few million years. But while they live, they dominate their environment. These massive stars are both creators and destroyers. Their radiation is eroding the pillars, yes, but it's also compressing the gas, potentially triggering star formation that wouldn't have occurred otherwise. The pressure they exert on the cloud fragments it, creating dense regions where gravity can take over. Without these massive stars, the pillars might not exist at all. There's an interesting temporal paradox associated with the pillars of creation. Because the Eagle Nebula is 7,000 light-years away, the light we see from the pillars left them 7,000 years ago. We're seeing the pillars not as they are now, but as they were when human civilization was just beginning to develop agriculture, when the Great Pyramids of Egypt were still thousands of years in the future. In fact, some scientists have suggested that the pillars might already be gone. There's evidence that a supernova exploded in the Eagle Nebula about 6,000 years ago. If that's true, the shock wave from that explosion might have already reached the pillars, dispersing them. But we won't see that happen for another 1,000 years, when the light from the event finally reaches Earth. So we're looking at pillars that might no longer exist, seeing a snapshot of a moment 7,000 years ago, waiting to find out if they survived or were destroyed by an event we haven't yet witnessed. It's a reminder of the strange relationship we have with cosmic distances, where space and time become intertwined, where looking far away means looking into the past. The pillars of creation are not unique. Similar structures have been found in other star-forming regions. The Eagle Nebula itself contains other pillars, visible in wider field images, and observations of different nebulae have revealed countless other examples of dense molecular clouds being sculpted by radiation from nearby stars. But there's something about these particular pillars that resonates. Perhaps it's their scale, the almost impossibly tall columns reaching into space. Perhaps it's their appearance, the way they seem almost architectural, like constructed monuments rather than natural formations. Or perhaps it's simply that they were the first such structures we saw in detail, captured in an image so striking that it immediately became iconic. Whatever the reason, the pillars of creation have become symbols. Symbols of star formation, of cosmic creation, of the dynamic processes that shape the galaxy. They represent the intersection of destruction and creation, showing us how the same forces can both sculpt beauty and drive it toward dissolution. They also represent the power of observation, of human curiosity and ingenuity. The Hubble Space Telescope, launched in 1990 and still operating more than 3 decades later, has transformed our view of the universe. The Pillars of Creation image is just one of thousands of stunning observations Hubble has made, but it's perhaps the most famous, a testament to what we can see when we put our instruments above Earth's atmosphere and look out into the cosmos with sensitivity and precision. As technology improves, as our telescopes become more powerful, we'll continue to study the pillars of creation and structures like them. The James Webb Space Telescope has already observed the pillars in infrared wavelengths, revealing details that were invisible to Hubble, showing the protostars within the pillars more clearly, mapping the distribution of gas and dust with unprecedented precision. Each new observation adds to our understanding. Each new image reveals something we didn't know before. And slowly, piece by piece, we build up a more complete picture of how these structures form, how they evolve, what they mean for the larger story of star formation in the galaxy. The pillars stand in the darkness, tall and patient, being created and destroyed simultaneously, sheltering new stars in their depths, glowing at their edges where radiation strips away their substance. They are monuments to impermanence, to the beautiful transience of cosmic structures. As you drift into sleep tonight, imagine those pillars, those vast columns of gas and dust, rising through space. Imagine the young stars hidden within them, growing slowly, preparing to emerge. Imagine the ultraviolet light streaming from nearby stars, sculpting, shaping, gradually eroding what it illuminates. Think about how creation and destruction are not opposites, but partners. How beauty can exist in the process of change. How even temporary things can leave permanent impressions. The pillars of creation stand, for now, in the Eagle Nebula, 7,000 light-years away, visible and magnificent, a snapshot of cosmic creation frozen in time, waiting for us to observe, to wonder, to understand. In the constellation Orion, just south of the leftmost star in Orion's belt, there's a dark silhouette rising against a backdrop of glowing gas. It looks like the head and neck of a horse, perfectly profiled, as if a celestial sculptor had carved it from the darkness itself. This is the Horsehead Nebula, one of the most photographed and beloved objects in the night sky. The Horsehead is a dark nebula, a dense cloud of dust and molecular gas that blocks the light from the Emission nebula behind it. That background nebula, cataloged as IC 434, glows red with the characteristic hydrogen alpha emission we've discussed before, ionized by nearby stars. Against this crimson glow, the Horsehead appears as pure darkness, a shadow, an absence of light. But that darkness is misleading. The Horsehead isn't empty. It's full of matter, dense with dust and gas, cold and opaque. Within its depths, molecules are forming, chemistry is happening, and the conditions for future star formation are slowly developing. The darkness we see is evidence of substance, not absence. The Horsehead Nebula is relatively small as cosmic structures go. From the top of the head to the base of the neck, it measures about 3.5 light-years. That's roughly the distance from our Sun to the nearest star system. Small on galactic scales, but still incomprehensibly vast by human standards. The shape of the Horsehead is like the pillars of creation, no accident. It's being sculpted by radiation from nearby stars. The same forces that illuminate IC 434 are also photoevaporating the dark cloud, eroding it, carving it into its distinctive profile. The Horsehead is like an island of dense material in a sea of less dense gas, and that island is slowly being worn away by the radiation that surrounds it. If we could watch the Horsehead over millions of years, we would see it changing. The head is being eroded from the edges inward. The main, that wispy material at the top of the nebula, is gas that's being stripped away, torn off by the stellar winds and radiation. Eventually, the distinctive shape will be lost. The Horsehead will become unrecognizable, dispersed into formlessness. But for now, from our perspective in this particular moment of cosmic time, the silhouette is clear and beautiful. It's a shape that human minds can recognize, can relate to, can find meaning in. We see a horse's head where there is only cloud and chance, pattern-seeking creatures that we are, finding familiarity in the alien. The Horsehead is part of the larger Orion molecular cloud complex, a vast region of star formation that includes the Orion Nebula, the Flame Nebula, and numerous other clouds and nebulae. This entire region, stretching across much of the constellation Orion, is one of the most active star-forming areas in our local galactic neighborhood. The complex is relatively nearby, cosmically speaking, only about 1,500 light-years from Earth. This proximity makes it an ideal target for studying star formation. We can observe it in detail, see individual protostars, map the distribution of gas and dust, understand the processes that are converting cloud into stars. The star Alnitak, the easternmost star in Orion's belt, is the primary source of radiation illuminating IC 434 and eroding the Horsehead. Alnitak is a blue supergiant, approximately 20 times more massive than our Sun and about 250,000 times more luminous. It's a young star, perhaps only a few million years old, but because of its enormous mass, it's already in a relatively advanced stage of its evolution. Alnitak's intense ultraviolet radiation floods the region, ionizing hydrogen, causing IC 434 to glow and slowly eating away at the Horsehead. Without Alnitak and stars like it, the Horsehead would be invisible, just another dark patch in an already dark sky. It's the contrast between the bright Emission nebula and the dark cloud that makes the Horsehead visible and distinctive. Observations of the Horsehead in different wavelengths reveal different aspects of its nature. In visible light, we see the silhouette, the iconic shape against the red background. In infrared wavelengths, which can penetrate dust, we can see into the nebula, revealing its internal structure, showing how the density varies, mapping the cooler regions where molecules accumulate. Radio observations detect molecular emissions, particularly from carbon monoxide, which serves as a tracer for the more abundant, but harder to detect, molecular hydrogen. These observations help us understand the total mass of the nebula, the temperature of the gas, the motions within the cloud. Each wavelength tells a different part of the story. Visible light shows us shape and context. Infrared reveals hidden structure. Radio maps the molecular content. X-rays might reveal embedded protostars or shock-heated gas. Together, these multi-wavelength observations create a complete picture, showing the Horsehead not as a static silhouette, but as a dynamic, three-dimensional structure embedded in a complex environment. The edge of the Horsehead, where it meets the ionized gas of IC 434, is a particularly interesting region. This boundary is where the photoevaporation is most active, where the dark cloud is being converted into ionized gas, where matter is transitioning from one state to another. It's a thin shell, a frontier between darkness and light. At this boundary, the physics is complex. The incoming ultraviolet radiation heats the surface of the cloud, raising its temperature. This heated gas expands and flows away, carrying material with it. The process is self-regulating to some extent. As material is removed, denser layers underneath are exposed, and the erosion continues. This photoevaporative flow creates interesting structures at the cloud's edge. Long, thin filaments of gas stream away from the Horsehead, visible in high-resolution images as delicate wisps and streamers. These are traces of the erosion process, captured in a moment, showing how the nebula is losing material to its environment. The interior of the Horsehead is cold. Temperatures there are only about 10 to 20 degrees above absolute zero, far colder than the coldest place on Earth, colder than the cosmic microwave background radiation that fills the universe. In this frigid environment, molecules can form and survive. Water ice coats dust grains. Carbon monoxide, ammonia, and more complex molecules accumulate. This molecular richness is important for future star formation. When and if portions of the Horsehead collapse to form stars, these molecules will be incorporated into the protoplanetary disks around those stars. Some might eventually become part planets, moons, comets. The chemistry happening in the Horsehead now could seed the chemistry of future worlds. But star formation in the Horsehead itself appears to be limited. The nebula is dense enough that stars could potentially form, but observations haven't revealed active star formation happening within it right now. Perhaps the erosion is proceeding too quickly, dispersing the cloud before gravity can pull regions together enough to trigger collapse. Or perhaps conditions just aren't quite right, the density not quite high enough, the temperature not quite low enough. The Horsehead is a favorite target for astrophotographers, both professional and amateur. Its distinctive shape, its position near the easily located Orion's belt, and the contrast between dark and bright make it an irresistible subject. Thousands of images of the Horsehead have been captured, each one slightly different, each one representing hours of careful observation, image processing, and dedication. For amateur astronomers, the Horsehead is challenging. It's faint, requiring dark skies, sensitive equipment, and long exposures to capture. But that challenge is part of its appeal. Successfully imaging the Horsehead is a milestone, an achievement that represents growing skill and understanding. Professional observatories have also studied the Horsehead extensively. The Hubble Space Telescope has observed it multiple times, creating detailed images that reveal structure invisible to ground-based telescopes. The Herschel Space Observatory mapped the Horsehead in far-infrared wavelengths, showing the distribution of cold dust. The Atacama Large Millimeter Array has observed molecular emissions, mapping the cloud in 3 dimensions. Each new observation adds detail, reveals something previously unknown. We learn about the density structure, the temperature gradients, the molecular composition, the magnetic fields threading through the cloud. Slowly, observation by observation, we build understanding. There's something poignant about the Horsehead's impermanence. This shape, which has become so iconic, so recognizable, won't last. In astronomical terms, it's already in the process of being destroyed. Future generations, millions of years from now, won't see a horse's head in Orion. They'll see something different, whatever shape the ongoing erosion happens to create, or perhaps nothing at all if the cloud is completely dispersed. But in another sense, the Horsehead has already achieved a kind of permanence. It exists in our images, our data, our understanding. We've documented it thoroughly, studied it extensively. Whatever happens to the actual cloud, we've preserved its form, captured this moment of its existence. This is part of what astronomy does. It freezes moments in cosmic time, creating records of structures and events that may be long gone by the time the light reaches us, or may change before we can observe them again. Each observation is a snapshot, a data point in the ongoing evolution of the universe. The Horsehead reminds us that what we see in the night sky is temporary. The constellations will change over millions of years as stars move through the galaxy. Nebulae will evolve, disperse, be replaced by new ones. Even the stars themselves are temporary, living for a while and then ending, returning their material to space. But in the present moment, in our time, the Horsehead is there, a dark silhouette against glowing gas, shaped by chance and physics into a form we recognize, a cosmic Rorschach test that happens to resemble something familiar. As you settle into sleep tonight, think about that dark horse rising in Orion. Think about the cold, dense gas within it, the molecules forming on dusk grains, the slow erosion happening at its edges. Think about how something can be both substantial and ephemeral, both solid and temporary. Think about how the universe creates forms that resonate with us, not because they were designed for us, but because we're part of the same universe, shaped by the same forces, made of the same material. The Horsehead stands in silence, a dark monument in a glowing field, temporary and beautiful, unknowingly iconic, patiently waiting to be dispersed, to join the greater flow of matter through the galaxy, to become part of whatever comes next. There's a nebula you can see with your own eyes tonight, if the sky is clear and you know where to look. No telescope needed, no special equipment, just your eyes and a dark enough sky. It appears as a fuzzy patch in Orion's sword, that line of stars hanging below the three bright stars of Orion's belt. This is the Orion Nebula, the closest massive star-forming region to Earth, and one of the most studied objects in the entire sky. The Orion Nebula is designated Messier 42, or M42, in the catalog compiled by French astronomer Charles Messier in the 18th century. Messier was a comet hunter, and he created his catalog to list fuzzy objects that weren't comets, objects that might confuse other comet hunters. He had no idea what most of these objects actually were, but his catalog has endured, and M42, the Orion Nebula, is one of its most spectacular entries. At a distance of approximately 1,344 light-years from Earth, the Orion Nebula is remarkably close in cosmic terms. This proximity makes it an invaluable laboratory for studying star formation. We can observe it in extraordinary detail, resolving individual protostars, mapping the distribution of gas and dust, studying the physics of stellar birth in ways that wouldn't be possible for more distant regions. The nebula is vast. It spans about 24 light-years across, large enough to contain thousands of solar systems. And within this volume, stars are being born at a prodigious rate. Estimates suggest there are about 700 stars in various stages of formation within the visible nebula, with perhaps thousands more hidden in the darker, dustier regions surrounding it. At the heart of the Orion Nebula lies the Trapezium Cluster, a group of 4 very bright stars that are easily visible even in small telescopes. These stars, designated with letters from A to D, are young, hot, and massive. They're the primary sources of energy that illuminate the nebula, ionizing the gas, causing it to glow with that characteristic reddish hue. The trapezium stars are incredibly young. They're estimated to be less than 1 million years old, infants by stellar standards. Our Sun, at 4.6 billion years old, is more than 4,000 times older than these stars. And yet, despite their youth, the trapezium stars are already massive and luminous. The brightest of them, Theta 1 Orionis C, is about 40 times more massive than the Sun and roughly 200,000 times more luminous. These massive young stars have a profound effect on their environment. Their intense ultraviolet radiation ionizes the surrounding hydrogen gas, creating what's called an H2 region, a zone of ionized hydrogen. This ionization is what makes the nebula visible and colorful. Without the trapezium stars, the Orion Nebula would be dark, cold, and invisible to optical telescopes, just another molecular cloud among many. But the trapezium stars do more than just illuminate. Their radiation also heats the gas, creating pressure that pushes back against the cloud. Their stellar winds, streams of charged particles flowing outward from their surfaces, blow bubbles in the surrounding material. They're simultaneously revealing the nebula and beginning to disperse it beyond the 4 bright trapezium stars visible in small telescopes. There are actually several more members of the cluster, visible only in larger instruments or at other wavelengths. The cluster contains stars of various masses, from massive O-type stars down small red dwarfs and even brown dwarfs, failed stars that never accumulated enough mass to ignite hydrogen fusion. The Orion Nebula is a complex, layered structure. The bright central region that's visible to the naked eye is actually just the inner edge of a much larger molecular cloud complex. This cloud, called the Orion Molecular Cloud, extends for hundreds of light years and contains enough material to create hundreds of thousands of stars. The visible nebula is essentially a cavity carved into this larger cloud by the radiation and winds from the trapezium stars. We're seeing the illuminated inner surface of this cavity, the walls glowing with ionized gas. Behind those walls, hidden from direct view, the molecular cloud continues, dense and dark, with ongoing star formation occurring in its depths. One of the most fascinating aspects of the Orion Nebula is the presence of protoplanetary disks around many of the young stars. These disks, called proplyds, short for protoplanetary disks, are the birthplaces of planetary systems. They're flattened clouds of gas and dust orbiting young stars, the leftover material from star formation that will eventually coalesce into planets. Hundreds of proplyds have been identified in the Orion Nebula, making it a crucial testing ground for theories of planet formation. Some of these disks are large and massive, containing more than enough material to create planetary systems like our own solar system. Others are smaller, perhaps capable of forming only a few rocky planets. Many of the proplyds are being photoevaporated by the intense radiation from the trapezium stars. The ultraviolet light heats the outer layers of the disk, causing the gas to stream away into space. This creates distinctive teardrop shapes, with the disk oriented perpendicular to the direction of the trapezium stars, and a tail of evaporating material streaming away. This photoevaporation is a race against time. Can planets form in these disks before all the material is stripped away? In some cases, probably yes. The inner parts of the disks, where rocky planets might form, are denser and more resistant to evaporation. But the outer regions, where giant planets might otherwise form, could be entirely dispersed before planets can accumulate. This suggests that planetary systems forming in regions like the Orion Nebula, near massive stars, might be different from systems that form in quieter environments. They might be more likely to have rocky inner planets, but lack the gas giants that exist in our outer solar system. The colors of the Orion Nebula are striking. In photographs, it appears as a swirl of reds, greens, blues, and purples. These colors represent different elements and different temperatures. The predominant red comes from hydrogen alpha emission, hydrogen atoms recombining and emitting light at a wavelength of 656 nanometers. The greens and teals come from oxygen, ionized at different states and emitting at different wavelengths. Blues can come from scattered light or from other atomic transitions. But here's an interesting fact. If you looked at the Orion Nebula with your own eyes, you wouldn't see these vibrant colors. Our eyes aren't sensitive enough to see faint nebular emission in color. The nebula would appear mostly greenish-gray, perhaps with hints of pink or blue in the brightest regions, but nothing like the technicolor splendor of long-exposure photographs. This isn't deception on the part of astrophotographers. The colors are real. The different wavelengths are truly being emitted. It's just that cameras can collect light over minutes or hours, accumulating enough photons to reveal colors that our eyes, seeing only the instant-by-instant flow of light, cannot perceive. The structure of the Orion Nebula is complex. There are bright regions and dark regions, filaments and knots, cavities and dense clouds. Some of this structure is created by the radiation and winds from the trapezium stars. Some is intrinsic to the original molecular cloud, variations in density that existed before the stars formed. Dark lanes of dust cut through the nebula, silhouetted against the brighter regions. These lanes are denser concentrations of material, thick enough to block the light from behind them. They're similar to the Horsehead Nebula in nature, just less distinctively shaped. And within these dark lanes, additional star formation might be occurring, hidden from view. The Orion Nebula has been known since ancient times, though early observers didn't understand what it was. The Mayans apparently knew of it, though references are ambiguous. It was certainly known to European astronomers by the early 17th century. Galileo may have observed it with his telescope, though he didn't comment on it specifically in his writings. The first detailed telescopic observations were made in the 1650s, and by the 18th and 19th centuries, the Orion Nebula was a favorite target for astronomers. It was bright enough to study in detail with the telescopes of the time, and its complex structure provided endless fascination. In the 20th century, the Orion Nebula became one of the first objects to be studied with the new techniques of astrophysics. Spectroscopy revealed what elements were present. Photography allowed the structure to be mapped in detail. Radio astronomy detected molecular emissions from the surrounding cloud. And with the advent of space telescopes, free from Earth's distorting atmosphere, the nebula could be observed with unprecedented clarity. The Hubble Space Telescope has observed the Orion Nebula extensively, creating detailed mosaics that reveal individual stars, proplyds, and structures too small to see from the ground. The Spitzer Space Telescope observed it in infrared, penetrating the dust to see embedded protostars. The Herschel Space Observatory mapped the coal dust. The Atacama Large Millimeter Array has studied molecular emissions at high resolution. Each new observation, each new wavelength, each new instrument reveals something previously unknown. We discover new protostars, new structures, new details about the physical conditions in the nebula. Our understanding grows, layer upon layer, observation upon observation. The Orion Nebula is dynamic, constantly changing, though the changes occur on timescales too long for us to notice directly. The stars are evolving, growing from protostars to main sequence stars. The proplyds are being photoevaporated, losing mass. The gas is flowing, expanding, being sculpted by radiation and winds. In a few million years, the nebula will look different. In 10 million years, it might be unrecognizable, but it will still be forming stars. The larger Orion molecular cloud contains enough material to sustain star formation for millions of years. As the current generation of stars disperses the visible nebula, new regions in the surrounding cloud will collapse, forming the next generation. The cycle will continue. There's something profound about being able to see the Orion Nebula with our own eyes. This isn't a remote, distant object visible only through powerful telescopes. It's right there, in a constellation that's familiar to people all over the world, visible to anyone who cares to look up on a winter evening. Knowing what it is makes the view more meaningful. That fuzzy patch isn't just a smudge of light. It's a stellar nursery, a place where stars are being born right now, where planetary systems are forming, where the future of the galaxy is being shaped. And we can see it spanning about 1 degree of sky, roughly twice the diameter of the full moon. As you rest tonight, think about the Orion Nebula hanging in the winter sky. Think about the trapezium stars at its heart, flooding the region with light and energy. Think about the hundreds of protostars scattered throughout the nebula, slowly growing, accumulating mass, moving toward the moment when fusion will ignite. Think about the protoplanetary disks, those flattened clouds where planets are beginning to form. Perhaps in some of those disks, billions of years from now, life will emerge. Perhaps beings will look up at their own night sky and wonder about the stars, just as we do. The Orion Nebula shines in the darkness, close and accessible, a reminder that the universe's grandest processes are happening not in some impossibly distant realm, but in our own galactic neighborhood, visible and beautiful, waiting to be observed and understood. On July 4th, 1054, astronomers in China observed something extraordinary. A new star appeared in the sky, in the constellation we now call Taurus. It was so bright that it could be seen during the day for 23 days. At night, it was bright enough to read by. The Chinese called it a guest star, and they carefully recorded its appearance and gradual fading over the following months. What those medieval astronomers witnessed was a supernova, the catastrophic death of a massive star. And nearly 1,000 years later, we can still see the remnant of that explosion. We call it the Crab Nebula, and it's one of the most studied and fascinating objects in the entire sky. The Crab Nebula lies about 6,500 light-years from Earth, in the direction of the constellation Taurus. It spans approximately 11 light-years across and is still expanding, growing larger with each passing year. The nebula is a chaotic tangle of filaments and wisps, glowing gases streaming outward from the explosion, carrying with them the elements forged in the star's core and in the supernova itself. But the Crab Nebula is more than just a remnant of an explosion. At its heart lies something even more remarkable, a pulsar, the collapsed core of the original star, now compressed into a sphere only about 20 kilometers across, but containing more mass than our entire sun. This pulsar is extraordinary. It rotates 30 times per second, spinning faster than a helicopter blade. And as it spins, it emits beams of radiation from its magnetic poles. These beams sweep across space like a lighthouse beam, and when they point toward Earth, we detect pulses of radio waves, X-rays, and even visible light, 30 times per second, with clockwork precision. The pulsar is the engine that powers the Crab Nebula. It pumps enormous amounts of energy into the surrounding gas, creating a wind of high-energy particles that flow outward at nearly the speed of light. This pulsar wind creates structures within the nebula, waves and ripples and shock fronts, features that change noticeably over periods of just months or years. In fact, the Crab Nebula is one of the few astronomical objects that shows visible changes on human timescales. Comparison of images taken years apart reveals that the filaments have moved, that structures have evolved, that the nebula is dynamic and active in ways that most celestial objects are not. The filaments in the Crab Nebula are the actual material ejected by the supernova, the outer layers of the original star blown into space at tremendous velocity. These filaments are rich in elements heavier than hydrogen and helium, oxygen, carbon, nitrogen, sulfur, and others. These are elements that were created inside the star during its lifetime, through nuclear fusion in its core. When we observe the Crab Nebula at different wavelengths, we see different aspects of its nature. In visible light, we see the filaments glowing from the heat and ionization caused by the pulsar's energy. In X-rays, we see the pulsar wind nebula, a bright region around the pulsar where the wind is most intense. In radio wavelengths, we see both the filaments and the overall structure of the expanding shell. The visible filaments appear in different colors depending on which elements are emitting light. Regions rich in hydrogen glow red. Areas with abundant oxygen appear greenish or bluish. Sulfur contributes deeper reds. Each color is a signature of composition, telling us what elements are present and in what quantities. The study of the Crab Nebula has been crucial to our understanding of supernovae and their remnants. Because we know when the supernova occurred, we have a precise aid for the nebula. This allows us to calibrate our models to understand how supernova remnants evolve over time. If we observe a supernova remnant of unknown age, we can compare it to the Crab Nebula and estimate how old it might be based on similar features. The Crab Nebula also taught us about pulsars. When pulsars were first discovered in 1967, they were mysterious. Radio telescopes were detecting regular pulses, ticks from space arriving with such precision that some scientists briefly wondered if they might be signals from alien civilizations. The objects were whimsically called LGM-1 for Little Green Men, but further observations revealed the truth. These were rapidly rotating neutron stars, the collapsed cores of massive stars, spinning and emitting beams of radiation. And one of the key pieces of evidence came from the Crab Nebula. Astronomers found that the nebula was pulsing in visible light, X-rays, and radio waves, all in perfect synchronization, all 30 times per second. The pulsar at the heart of the nebula was revealed. This discovery was profound. It confirmed that pulsars were associated with supernova remnants. It showed that the collapsed cores of massive stars could indeed become neutron stars. And it demonstrated that these objects could pump energy into their surroundings, powering nebulae for thousands of years after the initial explosion. The pulsar in the Crab Nebula is slowing down very gradually. Its rotation period is increasing by about 38 nanoseconds per day. That might not sound like much, but it represents a tremendous loss of rotational energy. That energy has to go somewhere, and it goes into the pulsar wind, into the particles and radiation that flow outward from the pulsar, energizing the nebula. Calculations show that the pulsar is losing rotational energy at a rate of about 100,000 times the total power output of our Sun. All of that energy is being pumped into a region only a few light years across. It's an extraordinary power source, and it's what keeps the Crab Nebula glowing brightly nearly 1,000 years after the explosion. The matter in a neutron star exists in a state unlike anything we can create on Earth. The density is so extreme that protons and electrons are crushed together, forming neutrons. A teaspoon of neutron star material would weigh about 1 billion tons. The surface gravity is so strong that if you could somehow stand on a neutron star, you would weigh billions of times more than you do on Earth. The magnetic field of the Crab pulsar is extraordinarily strong, trillions of times stronger than Earth's magnetic field. This intense magnetism is what channels the radiation into beams emanating from the magnetic poles. As the pulsar rotates, these beams sweep through space, and when they point our way, we see a pulse. The Crab Nebula is a reminder of stellar death, but it's also a reminder of cosmic creation. The elements ejected by the supernova, now spreading through space in the form of filaments and gas, will eventually mix with the interstellar medium. They'll become part of new molecular clouds, new star-forming regions. The carbon, oxygen, nitrogen, and other heavy elements from the Crab Nebula will be incorporated into future generations of stars and planets. In this way, the death of one star enables the birth of others. The cycle continues, matter flowing from stars to space and back to stars again, in an endless cosmic recycling program that has been operating for billions of years and will continue for billions more. The Crab Nebula has been observed by virtually every major telescope and observatory. It's a favorite calibration target because it's bright, it's well-studied, and it emits across the entire electromagnetic spectrum. When astronomers commission a new telescope or detector, they often observe the Crab Nebula first to verify that the instrument is working correctly and to calibrate its sensitivity. This means we have an extraordinarily detailed record of the Crab Nebula's appearance over time. We can compare images from decades ago with recent observations and see how the nebula has changed. We can track the motion of individual filaments, watch as structures evolve, observe the dynamic nature of this cosmic object. One of the most striking features of the Crab Nebula is the presence of wisps and waves in the inner regions, near the pulsar. These features are created by the pulsar wind interacting with the surrounding material. They're transient, lasting only months before changing or disappearing, replaced by new structures. It's like watching waves on an ocean, patterns that form and dissolve, driven by an underlying source of energy. The Crab Nebula is also a source of very high-energy particles called cosmic rays. These are charged particles, mostly protons and atomic nuclei, accelerated to enormous energies by the pulsar and its associated shock waves. Some of these particles escape the nebula and travel through the galaxy. It's possible, though unlikely, that some cosmic rays detected at Earth originated in the Crab Nebula. The study of the Crab Nebula continues to yield new discoveries. Recent observations have detected gamma-ray flares from the nebula, sudden brightening events at the highest energies. The mechanism producing these flares isn't completely understood, but they seem to be related to magnetic reconnection events in the Pulsar Wind Nebula, where magnetic field lines break and reconnect, releasing stored energy in bursts. The supernova that created the Crab Nebula was probably not the brightest supernova ever seen from Earth, but it's one of the best documented historically. Chinese astronomers recorded it, as did Japanese observers. There may have been observations from the Middle East as well. Curiously, there are no definite European records of the event, though Europe in 1054 was certainly capable of astronomical observation. Perhaps it was obscured by weather, or perhaps records were lost. The fact that we can connect a historical event, recorded by human observers nearly 1,000 years ago, with an object we can still see and study today, is remarkable. It bridges human history and cosmic timescales. Those Chinese astronomers, looking up at the bright guest star, had no idea what they were seeing. They couldn't have known it was an exploding star, or that it would leave behind a nebula and a pulsar. But they recorded what they saw, and that record allows us to date the event precisely. As you drift towards sleep, think about the Crab Nebula expanding through space. Think about the pulsar at its heart, spinning 30 times each second, beaming energy outward, powering the nebula with the rotational energy left over from its violent birth. Think about the filaments, the shreds of a star, enriched with heavy elements, slowly dispersing into space, destined to become part of new stars, new worlds, new possibilities. Think about how death and life, ending and beginning, are intertwined in the cosmos. How the death of one star creates the conditions for future stars to form. The Crab Nebula glows in Taurus, a monument to a stellar death witnessed by humans, a laboratory for studying the most extreme physics in the universe, a reminder that the cosmos is dynamic, violent, beautiful, and constantly transforming. Sometimes called the Eye of God for its appearance in photographs, the Helix Nebula is one of the closest planetary nebulae to Earth, and one of the largest in apparent size. Located about 700 light-years away in the constellation Aquarius, it spans roughly half a degree across the sky, about the same angular diameter as the full moon. But unlike the moon, the helix is faint. Its light is spread across that large area, giving it a low surface brightness that makes it challenging to observe visually, even though it's one of the brightest planetary nebulae in total light output. This is a common paradox in astronomy. Something can be intrinsically bright, but appear dim because that brightness is diluted across a large area of sky. The Helix Nebula, cataloged as NGC 7293, is the result of a sun-like star's death. Somewhere between 10,000 and 12,000 years ago, the star that created this nebula ran out of hydrogen fuel in its core. It swelled into a red giant, expanded to perhaps 100 times its original size, and then began to shed its outer layers in a series of gentle pulses. Those expelled layers are what we see now. They form a complex, three-dimensional structure that, from our viewing angle, appears as two overlapping disks or rings, creating the eye-like appearance. But this is a projection effect. The nebula isn't actually shaped like an eye. It's more like a cylinder or a barrel, and we happen to be looking at it almost directly down its axis. At the center of the helix is the remnant core of the original star, a white dwarf with a surface temperature of about 120,000 degrees Celsius, more than 20 times hotter than the sun's surface. This white dwarf is small, probably not much larger than Earth, but it contains about half the mass of the original star, compressed into that tiny volume. The white dwarf's intense ultraviolet radiation ionizes the expanding gas shells, causing them to glow. Different elements emit different colors. Hydrogen gives the characteristic red, oxygen creates the blue-green hues, and nitrogen adds to the mix. The result is a nebula that appears in photographs as a multicolored ring, though those colors are enhanced and exaggerated in most images. One of the most fascinating features of the Helix Nebula is the presence of thousands of tiny knots and filaments throughout the nebula. These structures, first clearly revealed in Hubble Space Telescope images from the 1990s, are called cometary knots because they have a distinct head-tail structure, like comets. Each cometary knot is larger than our entire solar system, typically about twice the diameter of Pluto's orbit. They're dense clumps of gas that are more resistant to the ionizing radiation from the central star than the surrounding material. As the ultraviolet light from the white dwarf hits these knots, it photoevaporates them, creating a tail of gas streaming away from the central star. The origin of these cometary knots is still debated. They might be density variations that existed in the original stellar atmosphere before it was expelled. They might be created by instabilities in the expanding gas, or they might form through some process we don't yet fully understand. What's clear is that they're common in the Helix and have been found in other planetary nebulae as well. The structure of the Helix Nebula is more complex than it first appears. The main, bright inner ring is surrounded by a fainter outer halo, material expelled earlier in the star's evolution. There are also jet-like structures extending from the central region, suggesting that the mass loss wasn't perfectly spherical but had some asymmetry. This asymmetry might be due to the star's rotation, or to magnetic fields, or to the presence of a companion star. Many planetary nebulae show evidence of binary companions, unseen stars orbiting the central white dwarf, and it's possible that the Helix harbors such a companion, though none has been definitively detected. The gas in the Helix is expanding at about 30 kilometers per second. That's slow compared to supernova ejecta, which can reach thousands of kilometers per second, but it's still fast by everyday standards, about 100,000 kilometers per hour. At this rate, the nebula will continue to expand and disperse over the coming millennia. Eventually, perhaps in another 10,000 or 20,000 years, the nebula will have expanded so much that it becomes too diffuse to see. Its material will merge with the general interstellar medium, mixing with gas and dust from other sources, potentially becoming part of new molecular clouds where future stars will form. The white dwarf at the center will continue to exist for much longer. White dwarfs cool very slowly, radiating away their residual heat over billions of years. The Helix's central star is currently very hot, but in a billion years it will have cooled considerably. In 10 billion years, it might be a black dwarf, a theoretical object that's cooled to the point where it no longer emits significant visible light. But we've never observed a black dwarf. The universe isn't old enough yet for any white dwarf to have cooled completely. Even the oldest white dwarfs, formed when the universe was young, are still radiating heat, still glowing, still warm enough to emit light. The Helix's central star will take longer than the current age of the universe to become truly cold and dark. The Helix Nebula has been studied extensively at multiple wavelengths. In visible light, we see the ionized gas, the shells and rings and cometary knots. In infrared, We can detect cooler dust that's mixed with the gas, dust that radiates in infrared wavelengths, even though it's too cool to produce visible light. In ultraviolet, we see the hottest regions, areas where the radiation from the central star is most intense. Radio observations can detect molecular emissions, particularly from carbon monoxide and other molecules that exist in the cooler, outer regions of the nebula. These molecules formed in the atmosphere of the original star before it expelled its outer layers, and they've survived in the outflowing gas, though they're gradually being dissociated by the radiation. The Helix is a popular target for amateur astrophotographers because of its size and brightness, though capturing it well requires skill. Wide-field imaging setups work best, able to frame the entire nebula. Long exposures are needed to bring out the faint outer regions and the subtle color variations. The result, when done well, is stunning. The cosmic eye staring back from the depths of space. For observers using telescopes visually, the Helix presents a challenge. It's faint and diffuse, easily washed out by light pollution or moonlight. Dark skies are essential. Even then, it doesn't look like the photographs. It appears as a pale, ghostly ring, subtle and elusive, requiring averted vision and patience to see clearly. But knowing what you're looking at makes the view meaningful. That faint ring isn't just a smudge of light. It's the outer layers of a star expelled into space, a star that lived for billions of years and is now in its final stages, its core cooling, its atmosphere dispersed, its planetary system, if it had one, destroyed or severely disrupted. If the Helix's progenitor star had planets, what happened to them? Any inner planets would have been engulfed when the star swelled into a red giant. They would have spiraled inward, friction with the star's extended atmosphere, dragging them down until they were consumed. Outer planets might have survived, though their orbits would have been altered by the star's mass loss. Some white dwarfs show evidence of planetary material, detected through spectroscopy or through the observation of dusty debris disks. It's possible that the Helix's white dwarf has such a disk, remnants of destroyed planets or asteroids, but detailed observations would be needed to confirm it. The Helix Nebula reminds us of the Sun's future. In about 5 billion years, our own star will undergo a similar transformation. It will exhaust its hydrogen fuel, swell into a red giant, and eventually expel its outer layers, creating a planetary nebula. Earth will almost certainly not survive this process. The planet will either be engulfed by the expanding sun or rendered completely lifeless. But that's so far in the future that it's almost meaningless to us now. The sun is still middle-aged, stable, with billions of years of steady burning ahead. The Helix shows us the end point, the fate that awaits. But it's a distant fate, one that our descendants, if any remain, will witness only after unimaginable spans of time. There's a certain peace to planetary nebulae like the Helix. Unlike supernovae, which are violent and catastrophic, planetary nebulae represent gentle endings. The star doesn't explode. It simply releases its outer layers, letting them drift away, exposing the core that sustained it for so long. It's a quiet conclusion to a long life, a transformation rather than a destruction. And in that transformation, the star returns material to space. The carbon, nitrogen, oxygen, and other elements created during its lifetime are now part of the nebula, spreading outward, mixing with the interstellar medium. This enriched material will eventually become part of new stars, new planets, continuing the cycle of cosmic chemistry. We are made of such material. The elements in our bodies were created in stars and dispersed by events like the one that created the Helix Nebula. Planetary nebulae from billions of years ago contributed to the chemical enrichment of the galaxy, making possible the formation of rocky planets and the emergence of life. The Helix is both an ending and a beginning, the end of one star's journey, but the beginning of a new chapter for the material it releases. Nothing is lost. Everything is transformed. As you settle into rest tonight, imagine the Helix Nebula floating in Aquarius. Imagine those expanding shells of gas, glowing softly in the darkness, studded with thousands of cometary knots, each one larger than our solar system, each one being slowly eroded by the light of the dying star. Imagine the white dwarf at the center, small and hot and alone, the compressed remnant of what was once a star like our sun, now entering the long, slow twilight of its existence. Think about endings that are also transformations, about conclusions that enable new beginnings, about how the universe wastes nothing, recycles everything, maintains the cycle of creation and dissolution across billions of years. The Helix watches from the southern sky, a cosmic eye, serene and ancient, a glimpse of stellar death rendered beautiful, a monument to impermanence, glowing quietly in the night. We've journeyed together through the nebulae, those cosmic clouds that populate our galaxy. We've seen them in all their variety: emission nebulae glowing with their own light, reflection nebulae borrowing radiance from nearby stars, dark nebulae hiding in shadow, planetary nebulae marking the gentle deaths of sun-like stars, and supernova remnants testifying to violent stellar endings. We've visited stellar nurseries where stars are being born, and we've witnessed the monuments left behind when stars die. We've seen pillars and horsehead shapes, eyes and crabs, rings and spirals, each nebula unique, yet all connected by the same fundamental processes, the same laws of physics, the same cosmic chemistry. But as we prepare to conclude this journey, it's worth taking a moment to reflect on what these nebulae mean, not just as astronomical objects, but as part of the larger story of the universe and our place within it. Every atom in your body has a history that spans billions of years. The hydrogen in your water molecules was created in the Big Bang, 13.8 billion years ago, in the first few minutes of the universe's existence. That hydrogen has remained fundamentally unchanged since then, passing through countless environments, perhaps incorporated into many different structures, but always remaining hydrogen. The heavier elements in your body have a different origin. The carbon that forms the backbone of every organic molecule, the calcium in your bones, the iron in your blood, the oxygen you breathe, none of these existed in the early universe. They were all created inside stars, through nuclear fusion in stellar cores. During a star's lifetime, fusion converts lighter elements into heavier ones. Hydrogen becomes helium. Helium becomes carbon and oxygen. In the most massive stars, the process continues, creating neon, magnesium, silicon, all the way up to iron. But fusion can only create elements up to iron efficiently. Creating anything heavier requires more energy than the reaction releases. So where do the heavier elements come from? From stellar deaths. When massive stars explode as supernovae, the enormous energy of the explosion drives fusion reactions that create elements heavier than iron. Gold, silver, platinum, uranium, all the elements at the bottom of the periodic table. These elements are created in the violence of the explosion and scattered into space. And where does all this ejected material go? Into nebulae. The expanding shells of supernova remnants are nebulae. The gentle expulsions from dying sun-like stars create planetary nebulae. All of this material, enriched with elements created in stellar cores and explosions, disperses into the interstellar medium, mixing with existing gas and dust. Eventually, this enriched material accumulates into new molecular clouds, new dark nebulae. Gravity pulls these clouds together, and they fragment into stellar nurseries where new stars form. Those new stars have a higher proportion of heavy elements than previous generations. They're more likely to form rocky planets, because rocky planets require heavy elements. Our Sun is a third-generation star, or perhaps even later. It formed from a molecular cloud that had already been enriched by multiple generations of stellar deaths. The cloud contained not just hydrogen and helium, but carbon and oxygen and silicon and iron, all the elements needed to make planets like Earth. When the Sun formed 4.6 billion years ago, it formed from a nebula. A stellar nursery not unlike the Orion Nebula or the Eagle Nebula, though probably smaller and less dramatic. That nebula contained the material from many previous stars, stars that had lived and died, stars that had created elements and expelled them into space. The rocky material in that nebula, the dust grains and molecules, accumulated into a disk around the young Sun. And from that disk, planets formed. The inner planets, Mercury, Venus, Earth, and Mars, formed from the rocky, metallic materials. The outer planets formed from ices and gases, growing large enough to capture hydrogen and helium from the disk. Earth condensed from this material. The iron that sank to form our planet's core, the silicates that make up the mantle and crust, the water that fills our oceans, the carbon dioxide in our atmosphere, all of it came from the protoplanetary disk, which came from the molecular cloud, which came from previous generations of stars and their nebulae. And life, when it emerged on Earth, was built from this stellar material. The first simple cells were made of carbon, nitrogen, oxygen, hydrogen, phosphorus, sulfur, all elements created in stars. As life evolved and diversified, it continued to use these same elements, arranging them in ever more complex patterns, but always working with the chemical building blocks provided by the cosmos. You're, quite literally, made of nebulae, made of stellar nurseries and planetary nebulae and supernova remnants. The atoms in your body have cycled through stars, through nebulae, through interstellar space, through the molecular cloud that formed the Sun, through the early Earth, through billions of years of geological and biological processes, and finally into you. Those atoms have been part of the ocean, part of mountains, part of dinosaurs and ancient forests and countless other organisms. And they'll continue after you. They'll return to the environment, be incorporated into other living things, remain part of Earth's cycles for billions of years, until eventually, perhaps, when the Sun dies and creates its own planetary nebula, they'll be expelled back into space to become part of new nebulae, new stars, new worlds. This is the cosmic connection. We're not separate from the universe, observing it from the outside. We're part of it. We're made of it. The same processes that create nebulae and stars also created us. The same elements that glow in distant clouds also flow through our veins. When you look up at the night sky, when you observe a nebula through a telescope or in a photograph, you're not looking at something alien and unrelated. You're looking at family, distant family, perhaps separated by light years and billions of years, but family nonetheless. You're seeing the environments where the material that makes you is created, processed, and prepared. The nebulae are beautiful, yes, but they're also meaningful. They're part of our story. The story doesn't begin with Earth, or with the solar system, or even with the Milky Way galaxy. It begins with the Big Bang, continues through generations of stars and nebulae, and leads eventually to us, to consciousness, to the ability to look back and understand. We are the universe becoming aware of itself. We're collections of atoms that were created in stars, expelled in nebulae, gathered into planets, and organized into complex structures capable of thought, of wonder, of asking questions about origins and meaning. And we're not the end of the story. We're just a chapter. The story continues beyond us. The Sun will eventually die, creating a planetary nebula. That nebula will disperse its material into space. That material will become part of new molecular clouds, new stellar nurseries. New stars will form, perhaps with new planets, perhaps with new life, new forms of consciousness that will look up at their own skies and ask their own questions. The cycle is endless. Matter flows from stars to nebulae to stars to nebulae, endlessly recycled, endlessly transformed. The universe creates, destroys, and creates again in a pattern that has continued for billions of years and will continue for billions more. But in this moment, in this particular arrangement of atoms, in this brief window of time, we exist. We're aware. We can observe the nebulae, understand them, appreciate their beauty and their significance. We can trace our origins back through the cosmos, connecting ourselves to the largest scales of space and time. There's something both humbling and elevating about this perspective. Humbling because we're so small, so temporary, brief flickers in the cosmic timescale, but elevating because we're connected to everything, participants in processes that span the universe, made of ancient starlight, capable of comprehending our own origins. The nebulae continue their slow evolution, indifferent to our existence, operating on timescales that dwarf human history. Stars are being born in stellar nurseries. Dying stars are creating planetary nebulae. Supernova remnants are expanding through space. Dark nebulae are hiding future stars in their depths. All of this has been happening for billions of years before we existed, and it will continue for billions of years after we're gone. But right now, in this moment, we're here to witness it, to understand it, to marvel at it. As you drift into sleep tonight, carry with you this knowledge. You're stardust. You are nebula material, organized into a form capable of contemplating its own origins. The atoms that make you have journeyed across billions of years and trillions of miles to be here, in this configuration, experiencing this moment. You're a temporary pattern in the cosmic flow, a brief arrangement of stellar material that will eventually dissolve back into the universe, to be rearranged into new forms. But for now, you exist, aware and wondering, connected to everything that is, was, and will be. The nebulae glow in the darkness, stellar nurseries and monuments to stellar death, beautiful and eternal in their impermanence, spinning out the cosmic story in gas and dust and starlight. And you are part of that story. You always have been. You always will be. Rest now in that knowledge. Rest in the comfort of connection. Rest knowing that you are not separate from the cosmos, but an integral part of it, made of the same material as stars and nebulae, participating in the same grand cycle of creation and transformation. The universe breathes through you. The stars shine in you. The nebulae live in every atom of your being. You are the cosmos, experiencing itself, understanding itself, appreciating its own beauty. And that is a profound and wonderful thing. Sleep well, child of the stars. Sleep well, product of nebulae. Sleep well, knowing you are made of light and wonder, temporarily arranged into this particular form, but forever part of the eternal cosmic dance. The nebulae drift through space, patient and beautiful, creating and destroying, beginning and ending, forever cycling, forever transforming, forever connecting us to the vast and ancient universe that is our home. Good night.